The spacecraft rests motionless on the launch pad, taller than many buildings, and so heavy that most of its mass will disappear within the first few minutes. Enormous fuel tanks surround a small compartment where human beings sit and wait. Above them is a sky in which the naked eye makes the stars appear as though they have all been fixed to the same flat surface. But the nearest star beyond the Sun is more than 4 light-years away. Even light, traveling at nearly 300,000 kilometers per second, needs more than 4 years to cross that distance. The spacecraft's destination is not the Moon, Mars, or the edge of the solar system. It is heading toward another star. To reach one within a human lifetime, it would need to travel faster than any vehicle ever built, endure more than any machine ever operated, and remain more self-contained than any artificial habitat that has ever existed. Welcome to Night Cosmos Sleep. Tonight, we will not ask whether humanity has enough courage to travel to the stars. We will ask a more difficult question. How far do the laws of physics allow such a journey to go? And at what point does the universe begin imposing limits that cannot be negotiated? On Earth, every breath is supported by an entire planet. The atmosphere maintains pressure. The oceans store heat. The magnetic field deflects some charged particles. Millions of living species participate in the cycles of water, carbon, and nutrients. An interstellar spacecraft would have to compress many of those planetary functions inside a metal shell. It would need to carry air, water, food, repair materials, medical equipment, and an energy source capable of operating for decades. It would have to protect human beings from radiation, interstellar dust, and the heat produced by its own machinery. It would also need fuel to accelerate, followed by some way to slow down when it reached its destination. Otherwise, it would simply pass through the target star system within a matter of hours and continue disappearing into the darkness. But the greatest difficulty does not lie in any single component. It lies in the way every problem connects to every other problem. A thicker shield makes the spacecraft safer, but also heavier. A heavier spacecraft requires more energy. More energy produces more heat. A larger cooling system adds still more mass. Every solution creates a new cost somewhere else. If we try to overcome these problems by traveling faster, the environment ahead changes in nature. A hydrogen atom that would normally be almost harmless could strike the front of the spacecraft like a particle of high-energy radiation. A grain of dust, smaller than the tip of a needle, could release energy comparable to a large explosion at the exact point of impact. Space does not need to be filled with matter. The spacecraft only needs to move through that thinly scattered matter fast enough. If we choose to travel more slowly, the danger from collisions decreases, but the journey becomes longer. The spacecraft must then survive beyond the lifetimes of the people who first boarded it. Children may be born between the stars, grow up beneath artificial lights, and learn about oceans as a historical concept. At that point, the journey is no longer transportation. It becomes a biological, social, and ethical experiment lasting across generations. Even communication cannot save them in the familiar way. A signal sent to the nearest star takes more than 4 years to arrive. A reply requires more than 4 additional years to return. By the time advice reaches the spacecraft, the emergency may already have been resolved. The person who asks may be nearly a decade older, and society on Earth may have entered a different era. And if the spacecraft approaches the speed of light, time no longer accumulates in the same way for those traveling and those who remain behind. The passengers may experience a shorter journey, but Earth will age much more. Technology may allow humanity to cross the distance, but it cannot keep every place within the same present. Eventually, even a civilization that survives for millions of years would encounter a limit greater than any spacecraft. The space between galaxies is expanding. There are regions whose ancient light can still reach us, yet a signal sent today may never catch up with them. A place may remain visible while no longer existing within a future we can ever reach. The spacecraft on the launch pad has not yet moved. and yet the entire journey is already governed by laws that existed long before humanity appeared. Rockets, fuel, shielding, and artificial ecosystems are only the tools we use to negotiate with those laws. The engines begin to ignite. The ground trembles. During the next few minutes, the spacecraft will complete the easiest part of an interstellar journey, leaving the surface of Earth. A rocket standing upright on a launch pad creates the impression that its goal is simply to go upward. But to enter orbit, altitude is not the most important factor. A spacecraft can reach the edge of space and still fall straight back down. To remain above Earth, it must move sideways fast enough that, while gravity pulls it downward, the curved surface of the planet continually falls away beneath its path. Orbit is therefore not a place where gravity disappears. It is a state of continuous freefall. The space station, the astronauts, and every object inside are all falling around Earth together. Because the floor is not supporting their bodies the way it does on the ground, they experience what feels like near weightlessness. In low Earth orbit, the required speed is about 7.8 kilometers per second. At that speed, an object could travel from Hanoi to Ho Chi Minh City in only a few minutes if it moved in a straight line above the ground. But a rocket cannot accelerate however it chooses. It must pass through the atmosphere, overcome drag, work against gravity, and keep its structure from being torn apart. Earth's escape velocity near the surface is about 11.2 kilometers per second. This does not mean that an engine only needs to push a spacecraft to exactly that speed, and then every problem disappears. The orbit, direction of travel, atmospheric drag, and starting position all affect the journey. Even so, the number reveals how deep Earth's gravitational well really is. Imagine throwing a ball upward. It slows down, stops, and falls back. Throw it harder, and it rises higher. Throw it fast enough in a horizontal direction, and it continues falling without ever reaching the ground. Throw it faster still, and the path opens so widely that the object never returns. The problem is that the human body represents only a tiny fraction of a rocket's total mass. Most of the vehicle consists of fuel, tanks, engines, and structures that will eventually be discarded. A large rocket may leave the ground weighing thousands of tons, while placing only a small fraction of that mass into orbit. This is not evidence of poor design. It is a consequence of the fact that a rocket must carry the material its engines will eject behind it. Unlike an airplane, a rocket cannot draw oxygen from the surrounding air once it climbs high enough. It must carry both fuel and oxidizer, while also lifting the tanks that contain them during the earliest phase of flight. When the engines first ignite, the rocket is at its heaviest. It must generate enough thrust to lift all of the unused propellant. With every passing second, part of that mass is expelled backward at tremendous speed. The vehicle becomes lighter, allowing the same engine to increase its velocity more rapidly during the later stages. This is why rockets are usually built in stages. Once a fuel tank is empty, the structure holding it is no longer useful. If the rocket continued carrying the empty shell, its engines would waste fuel pushing something that no longer served a purpose. Discarding the old stage makes the vehicle lighter, but it also reveals an important truth. Most of the enormous machine standing on the launch pad was never intended to reach the destination. Every stage that falls away is like part of a ladder being removed as soon as the climber has reached the next step. By the time the spacecraft reaches orbit, what remains is far smaller than the vehicle that once shook the ground. Low Earth orbit, however, is still extremely close to Earth on a cosmic scale. If Earth were reduced to a ball 1 meter across, the space station would orbit only about 3 centimeters above its surface. The moon would then lie nearly 30 meters away, while the nearest star would be thousands of kilometers in the distance. Leaving the launch pad is not the same as leaving the solar system. Even traveling beyond the moon's orbit would be only the beginning of a journey millions of times longer. What is remarkable is that Earth is both an obstacle and a shield. Gravity makes departure expensive in energy, but it also keeps the atmosphere and oceans from escaping. The atmosphere creates drag for rockets, but it also prevents most small objects and many forms of radiation from reaching the ground. The very things a rocket struggles to escape are also what allowed life to survive. As soon as the spacecraft climbs higher, the functions that were once free begin to carry a cost. Air must be contained within tanks and pipes. Water must be recovered. Heat must be carried toward radiators. Radiation must be slowed by shielding materials. Even a cabin the size of a small room requires an entire network of equipment hidden behind its walls. If a wall develops a hole on Earth, outside air rushes in. If the spacecraft's hull is punctured in a vacuum, the air inside escapes. If the air conditioning system stops working at home, the room becomes uncomfortable. If it stops aboard a spacecraft, heat and carbon dioxide can accumulate inside an environment with no window that can be opened. The spacecraft therefore carries more than human beings. It carries part of a planet in the form of machinery. When the final stage places the vehicle into orbit, the engines shut down. The roar no longer travels through the structure. Earth stretches below, covered by clouds and oceans. From that height, the atmosphere appears as only a thin glowing line. The entire history of complex life unfolded beneath that almost invisible membrane. But the spacecraft has still not begun its interstellar journey. It has reached a speed of only a few kilometers per second. To reach the nearest star within a few decades, it would need to travel thousands of times faster. And here, a limit deeper than gravity begins to appear. Not Earth's gravitational well, but the equation that forces a rocket to carry fuel for the fuel it has not yet burned. A rocket moves according to a very simple principle. It throws matter backward, so that everything remaining moves forward. What makes the problem difficult is not the principle itself, but the way the demand for fuel increases. The amount by which a rocket can change its velocity is known as delta V. This is not simply its maximum speed. It is the vehicle's total capacity to accelerate, slow down, and change direction. A spacecraft needs delta V to leave Earth orbit, correct its trajectory, approach its destination, and eventually come to a stop. The rocket equation tells us that delta V depends on the exhaust velocity and the ratio between the vehicle's initial mass and its mass after the fuel has been burned. What matters is that this relationship is logarithmic. If we reverse the question and ask how much fuel is required to achieve a larger delta V, the necessary mass ratio grows exponentially. This is where ordinary intuition begins to fail. Traveling twice as fast does not require only twice as much fuel. The additional fuel must also be accelerated, which means more fuel is needed to push it. That new fuel must then be pushed by still more fuel. The process repeats, causing the initial mass to increase extremely quickly. The best chemical engines expel gas at velocities of only a few kilometers per second. 1/10 the speed of light, by comparison, is nearly 30,000 kilometers per second. The difference between those numbers is not a factor of a few, but a factor of thousands. If we attempted to use an ideal chemical rocket to reach that velocity while carrying all of its fuel, the required mass ratio would become so enormous that the number would lose physical meaning. We cannot build a rocket containing more fuel than the amount of matter that could realistically be assembled, simply to push a small cabin to 10% of the speed of light. This is why interstellar travel cannot be achieved by building a larger version of today's rockets. The technology must change the way velocity is paid for. One option is to increase the exhaust velocity. If every kilogram of propellant is thrown backward more quickly, it produces a greater change in the spacecraft's velocity. Electric propulsion does this by using electric or magnetic fields to accelerate ions. These engines consume very little propellant and can operate for long periods, but they produce only a small amount of thrust. A lightweight probe can gradually accelerate over many months. A spacecraft carrying thousands of people would require far more thrust, making the power source and heat radiation system enormous. Nuclear energy provides far more energy per kilogram of fuel than chemical reactions. Nuclear fission splits heavy atomic nuclei. Nuclear fusion combines lighter nuclei, similar to the process that powers stars. In theory, fusion could expel material at much higher speeds and reduce the curse of mass. But a reactor is not an abstract block of energy. It requires magnets, reaction chambers, pipes, heat-resistant materials, control systems, and radiators. The fuel may contain a great deal of energy, but the machinery needed to convert that energy into thrust still has mass. Antimatter is even more impressive. When matter and antimatter meet, a very large portion of their mass can be converted into energy. Humanity, however, currently produces only microscopic quantities, while consuming far more energy than could ever be recovered. Storage would also require electromagnetic fields because antimatter cannot touch the walls of an ordinary container. Another idea is to leave the energy source behind. A light sail could be pushed by a laser beam transmitted from within the solar system. The vehicle would not need to carry fuel for acceleration. If the sail and probe were light enough, a large laser array might accelerate them to a significant fraction of the speed of light. But a beam of light spreads with distance. Keeping it focused on a small sail, millions of kilometers away becomes a problem involving optics, stability, and the size of the transmitting system. The sail must be thin enough to remain lightweight, yet nearly perfectly reflective, so that it does not melt. And at the destination, there would be no second laser array waiting to slow down the first arriving spacecraft. Another possibility is to gather fuel along the way by using an enormous magnetic field to collect interstellar hydrogen. The idea is attractive because the spacecraft would not need to carry all its fuel from the beginning, but interstellar gas is extremely thin. Gathering enough material would require an enormous interaction area, while the drag created by collecting particles could reduce the benefit. At high speeds, the incoming hydrogen itself becomes a source of radiation and heat. Every proposal attempts to escape the exponential penalty by changing one part of the problem: increasing exhaust velocity, reducing spacecraft mass, placing the energy source elsewhere, or gathering material during the journey. None of them eliminates the conservation of momentum or energy. The payload mass also cannot be reduced without limit. A probe may weigh only a few grams and transmit a small amount of data. A crewed spacecraft must contain shielding, water, food, living space, medical equipment, and repair systems. The more closely the vehicle resembles a habitable world, the harder it becomes to accelerate. Suppose the spacecraft only needs to accelerate and never slow down. When it reaches the target star, it will pass through the system at tens of thousands of kilometers per second. An entire planetary system could be crossed too quickly for careful observation, much less entry into orbit. To stop, the spacecraft must carry fuel or some other braking system. Fuel reserved for the final stage must be accelerated throughout the entire first stage of the journey. This makes the rocket equation even more unforgiving. The spacecraft must carry not only the means to create its velocity, but also the means to erase that velocity later. In interstellar spacecraft design, every kilogram carries an energy history. A liter of water does not simply need to be lifted away from Earth. It must be accelerated to cruising speed, protected from radiation, cooled or warmed when necessary, and then slowed down at the destination. If the journey includes a return trip, it must undergo the entire process again. The question, therefore, is not merely how powerful an engine we can build. The question is how much that engine must push, for how long, with how much heat, and how the spacecraft will still retain the ability to stop. The rocket equation does not forbid interstellar travel. It simply makes familiar approaches become absurd very quickly as the required distance and speed increase. To travel farther, humanity must use denser energy sources, lighter vehicles, longer travel times, or infrastructure built on a scale never attempted before. The imagined spacecraft leaves Earth orbit and turns toward the nearest star. Its new engine may continue operating for years. Its velocity rises little by little. Yet to the naked eye, the star ahead still appears no larger. The next obstacle is no longer fuel. It is a distance so vast that even the kilometer becomes a useless unit. There is one way to take advantage of orbital energy, commonly known as the Oberth effect. If an engine burns fuel while the spacecraft is already moving quickly near a planet or star, the same change in velocity can produce a larger change in orbital energy than a burn performed where the spacecraft is moving more slowly. This does not create energy from nothing. It takes advantage of the fact that the engine transfers energy, while the vehicle already has a high velocity within a gravitational field. Space probes have used close planetary flybys to change direction and gain or lose some orbital energy from a planet's motion around the Sunday. An interstellar spacecraft might take advantage of the Sun or the giant planets during the first stage of its departure, but the benefit would still be small compared with the delta V required to reach a meaningful fraction of the speed of light. Launching from the Moon or from space would also reduce part of the burden. The Moon has weak gravity, no thick atmosphere, and a lower escape velocity than Earth. An industrial base on the Moon could launch materials, fuel, or shielding with a lower energy cost. This suggests a more realistic path than a single rocket leaving the ground and traveling directly to another star. Humanity could build infrastructure in stages, mining materials from asteroids, producing fuel beyond Earth, assembling spacecraft in space, and operating enormous laser systems positioned closer to the Sunday. Interstellar travel may become the final product of an entire solar system economy rather than a single mission. The rocket on the launch pad would carry people and equipment only as far as an assembly site. The true interstellar spacecraft might never enter Earth's atmosphere at all. But building infrastructure throughout space would itself require centuries of experience, resources, and automated systems. It would transfer the difficulty from a single spacecraft to an entire civilization. The laws of physics would not disappear. The bill would simply be divided among a greater number of structures. The nearest star system beyond the Sun is Alpha Centauri. Its closest member to us is Proxima Centauri, about 4.24 light-years away. In the language of astronomy, it is a neighbor. In the language of travel, it is an abyss. A light-year is the distance light travels in 1 year, nearly 9.5 trillion kilometers. Multiply that number by more than 4, and the distance becomes so vast that expressing it in kilometers no longer helps human intuition understand it. Imagine shrinking the solar system. If the Sun were a ball 14 centimeters across, Earth would be only about 1 millimeter wide and would lie 15 meters away. Neptune would be roughly 450 meters from the Sunday. At that same scale, Proxima Centauri would not be at the far end of the room or even on the other side of the city. It would be more than 4,000 kilometers away. All the familiar planets, asteroids, and comets would become a small cluster surrounding the ball that represents the Sun, while the nearest star would lie on the other side of a continent. Voyager 1 is the most distant human-made object. It left Earth in 1977 and is now traveling outward from the solar system at about 17 kilometers per second relative to the Sunday. That is fast enough to circle Earth in less than an hour. But if it were heading directly toward Proxima Centauri, the journey would still take tens of thousands of years. This distance changes the meaning of durability. A machine that operates for 50 years is already a rare achievement. A probe traveling for 70,000 years would need to survive longer than every literate civilization that has ever existed. Not only its components, but the language, nations, and even the structure of the society that built it could disappear before it arrived. To complete the journey in 40 years, the average speed would need to exceed 1/10 the speed of light. That is approximately 30,000 kilometers per second. Not 30,000 kilometers per hour, but every second. At that speed, the spacecraft could travel from Earth to the Moon in about 13 seconds. It could cross the distance between Earth and the Sun in less than an hour and a half. Yet Proxima Centauri would still remain more than 40 years away, even if we ignored the time needed to accelerate and slow down. At 1% of the speed of light, the journey would require more than 400 years. At 0.1%, it would require more than 4,000 years. These numbers show why the idea of a generation ship does not arise, because humanity enjoys imagining life inside an enclosed cabin. It arises when achievable speeds remain far below those required to reach the destination within a single human lifetime. Distance also transforms the problem of navigation. The destination star does not remain still. It moves through the Milky Way, while its planets orbit around it. The spacecraft must aim for where the target will be in the future, not where it appears in the sky today. Light from Proxima Centauri takes more than 4 years to reach us. The image we observe today shows the system as it existed more than 4 years ago. Before launching a spacecraft, astronomers would need to measure the star's motion, predict its future position, and continually update the flight path throughout the journey. An extremely small angular error can grow into an enormous distance. If the direction of travel is wrong by only 1/1,000,000th of a radian, then after 4 light years, the spacecraft could miss its intended path by millions of kilometers. A tiny number on a control panel becomes the difference between reaching a planet and missing its entire surrounding region. At lower speeds, the spacecraft has more time to observe and correct its path. At extremely high speeds, reaction time becomes shorter. An obstacle detected too late may no longer be far enough away to avoid. A large spacecraft cannot change direction instantly because every course correction requires force and places acceleration on the structure. Distance also transforms communication into correspondence. A signal from Earth to Proxima Centauri takes 4.24 years to arrive. The fastest possible reply would return after a total of nearly 8.5 years. There could be no live conversation and no mission control guiding the crew step by step through an emergency. If the spacecraft were halfway there, a signal would need more than 2 years to reach Earth and more than 2 additional years to return. By the time the answer arrived, the damaged component would already have needed to be repaired, or the spacecraft would have failed. This is why distance is more than empty physical space. It weakens every form of support. A rescue spacecraft would face the same limits of speed. Supplies could not arrive faster than the vehicle already in danger. Experts on Earth could send knowledge only into the spacecraft's past. When the distance becomes great enough, autonomy is no longer a design choice. It is a condition of survival. The Milky Way makes Proxima Centauri appear close. The galaxy's disk is about 100,000 light-years across. If light had left one side of the Milky Way around the time modern humans first appeared, it might only now be reaching the other side. A civilization spread across the galaxy could not function like a single nation. News arriving from distant regions would always belong to the past. Every community would have to make decisions within its own present. But before considering a civilization on that scale, humanity must solve the nearest destination. 4 light-years may look small on an astronomical map, but they exceed the entire travel experience of our species. The obvious solution is to keep accelerating. But as velocity moves closer to the speed of light, nature no longer behaves like a road that allows a vehicle to travel as fast as its engine permits. Space and time begin to change the way they are measured, and the speed of light emerges not as an engineering record, but as a limit built into the relationship between cause and effect itself. In everyday life, velocities add together in an intuitive way. If someone walks forward inside a moving train, a person standing beside the track sees that person's speed as the speed of the train plus the speed of their steps. This calculation works extremely well whenever every motion involved is far slower than light. But if the person inside the train switches on a flashlight, both that person and the observer beside the tracks measure the beam of light traveling at the same speed through a vacuum. The outside observer does not see the light moving faster simply because its source is aboard a moving train. For this to be true, space and time cannot be absolute in the way Newtonian intuition once suggested. 2 people moving relative to one another may measure distances and time intervals differently, while still agreeing on the speed of light. Imagine a very simple clock. A beam of light travels up and down between 2 mirrors. Each completed round trip marks 1 tick. To someone standing beside the clock, the light travels straight upward and then straight downward. But to someone watching the clock move horizontally past them, the light must follow a longer diagonal path because the mirrors shift position while the light is traveling. Both observers still measure the same speed of light. Because the path is longer for the outside observer, the time between ticks must also be longer. The moving clock is measured as running more slowly. This is time dilation. It is not an illusion, and it is not an error in the equipment. Atomic clocks placed on airplanes, satellites, and the ground really do accumulate slightly different amounts of time. Satellite navigation systems must correct for relativistic effects so that the location displayed on a phone does not gradually drift out of position. For the passengers, nothing feels unusual. Their hearts continue beating normally. 1 second still feels like 1 second. The difference appears only when they compare their clock with another clock that followed a different path. Distance along the direction of motion is also measured differently. To the people aboard the spacecraft, the journey to the star may be shorter than the distance measured by observers on Earth. This phenomenon is known as length contraction. Time dilation and length contraction are not two separate forms of magic. They are the way space-time preserves the same speed of light for all observers moving at constant velocity. At 10% of the speed of light, the effect remains small. At 50%, it becomes clearer but is not yet overwhelming. At 90% of the speed of light, the time dilation factor is about 2.3. This means that if a period of steady travel lasts 23 years, according to Earth, the passengers experience about 10 years. At 99% of the speed of light, the factor rises above 7. 10 years aboard the spacecraft could correspond to more than 70 years in Earth's frame of reference. If we ignore the periods of acceleration and deceleration for the sake of a simple illustration, adding only another 9% of the speed of light, from 0, 90c to 0, 99c, causes the time dilation factor to increase by more than 3 times. As velocity approaches c, every small additional step becomes vastly more expensive. This can make an extremely long journey, both possible and painful, in a strange way. Travelers may cross an enormous distance within a shorter amount of their own time, while far more years pass at home. They are not traveling into the past. They are traveling into the future of those who remained behind. Why can matter never reach exactly the speed of light? The familiar statement that mass becomes infinite can be misleading. A more accurate explanation is that the energy and momentum required to continue increasing the velocity of an object with rest mass grow without limit as it approaches c. No finite amount of energy can bring it exactly to c. Photons travel at the speed of light, not because they were accelerated from rest. A photon does not have a rest frame in the way a spacecraft does. Ordinary matter cannot simply use a stronger engine and become a photon. The speed of light is also the limit for information. If an event occurs at Proxima Centauri, Earth cannot know about it until the signal arrives more than 4 years later. According to verified physics, there is no way to transmit instructions, warnings, or results faster than light. This is connected to causality. A cause must be able to occur before its effect. If information could travel arbitrarily faster than light, observers moving relative to one another might disagree about the order in which events occurred. In some descriptions, an answer could arrive before the question was asked. Nature appears to protect causal order by building the speed of light into the structure of space-time. For this reason, c is not like the speed of sound. A supersonic aircraft does not break the relationship between cause and effect. A faster-than-light signal would reach into a much deeper foundation of physics. Ideas such as wormholes and warp drives do not necessarily require a spacecraft to exceed c within its immediate surroundings. Instead, they attempt to alter the geometry of space-time and shorten the route. However, the best-known models usually require negative energy or exotic matter that we do not know how to create or maintain on the necessary scale. They are mathematical possibilities worth studying, not engineering solutions currently available. Quantum communication does not allow instantaneous messages either. Quantum entanglement creates profound correlations between measurements, but turning those results into usable information still requires an ordinary communication channel that cannot exceed the speed of light. Every realistic plan must therefore accept c as a limit. Matter with rest mass may approach it but cannot reach it, and the closer it comes, the more sharply the energy cost rises. Relativity offers one small consolation. The people aboard the spacecraft may experience a shorter journey, but it does not eliminate the energy required for acceleration. The radiation coming from ahead, the need to slow down, or the time that has passed on Earth. Two clocks are synchronized before departure. One remains in a laboratory. The other travels aboard the spacecraft. Both operate perfectly. When they meet again, they no longer display the same number. The universe allows passengers to bend their experience of time, but it does not give them the velocity required to do so for free. At relativistic speeds, the classical kinetic energy formula 1/2 the mass multiplied by the square of the velocity is no longer sufficiently accurate. The total energy is described using the Lorentz factor. When velocity rises from 0, 9c to 0, 99c, the spacecraft becomes only about 10% faster in absolute terms, but the energy required per kilogram increases by more than 3 times. At 0, 999c, the Lorentz factor exceeds 22. Each kilogram of matter carries kinetic energy equivalent to more than 20 times its own rest mass energy after the rest energy portion is subtracted. The spacecraft does not turn into energy, but the amount of kinetic energy accompanying it becomes enormous. The famous equation E equals mc squared shows that 1 kilogram of rest mass corresponds to approximately 9 times 10 to the 16th joules. Chemical reactions release only a tiny fraction of the energy stored in electron bonds. Fission and fusion draw a larger fraction from atomic nuclei, but they still do not convert all mass into useful energy. Even with a highly efficient source of energy, momentum must still be managed. A spacecraft cannot simply use energy and accelerate without interacting with anything. It must eject matter, emit photons, or receive force from an external beam. Energy and momentum appear together on the bill. A photon rocket represents an ideal limit. It emits light directly backward. Because photons carry momentum, the spacecraft moves forward without requiring reaction mass beyond the energy itself. But the thrust produced per watt is extremely small. Generating a force equal to the weight of 1 kilogram on Earth would require about 3 gigawatts of power from an ideal photon beam. Accelerating a large spacecraft at a meaningful rate would require power far beyond that of any present-day system. This number shows that high energy density does not automatically produce high thrust. An extraordinarily powerful generator could emit photons, but most of its energy would need to be directed with near-perfect precision, while the machinery would still have to survive the resulting heat. If the engine ejects matter at less than the speed of light, it may produce more thrust for the same power, but the spacecraft must carry or collect reaction mass. Every design lies somewhere along a trade-off between power, exhaust velocity, and the amount of propellant. A powerful engine, therefore, is not a single type of measurement. An engine with high thrust but poor propellant efficiency is useful for leaving a planet. An engine with high exhaust velocity but low thrust is better suited to gradual acceleration over long periods in space. An interstellar spacecraft may require several different systems for different stages of its journey. Let us place a specific number into the journey. Suppose a spacecraft has a mass of 1,000 metric tons, equivalent to 1 million kilograms. This would still be a very small vehicle if it had to carry an entire community, but it is large enough to reveal the scale of the energy involved. At 1/10 the speed of light, its kinetic energy would be approximately 4.5 times 10 to the 20th joules according to the classical approximation, which remains reasonably accurate at this speed. Written out in full, it is a number containing more than 20 digits. That energy is not the total cost. It is only the kinetic energy of the spacecraft after acceleration, assuming a perfect process with no losses. Stopping at the destination would require removing nearly the same amount of energy. A real engine would also produce heat, radiation, and other losses. If the spacecraft weighed 10,000 metric tons, the energy requirement would increase tenfold. If its speed doubled within the range where relativistic effects were not yet dominant, its kinetic energy would increase by nearly 4 times. Velocity is a more dangerous lever than mass. This explains why shortening the travel time quickly becomes so difficult. Traveling slightly more slowly may add many years to the journey, but traveling slightly faster can sharply increase the energy requirement, while also making collisions with gas and dust more dangerous. The energy source must do more than provide an enormous amount of power. That power must be converted into controlled motion in a specific direction. An explosion releases energy very quickly, but most of it spreads in every direction. An engine must transform a substantial portion of that energy into useful momentum without destroying the vehicle itself. If a remote laser beam is used, the transmitting system could extend across a large region of the solar system. If nuclear reactions take place aboard the spacecraft, then the reactor, fuel, and radiators must all be accelerated along with it. There is no method of storing or delivering energy that requires absolutely no mass or supporting infrastructure. Waste heat is the silent opponent. On Earth, machinery transfers heat into the surrounding air or water. In a vacuum, there is no natural flow of gas to carry heat away. The spacecraft can release heat only through electromagnetic radiation, primarily in the infrared. Radiated power increases very rapidly with surface temperature. A hotter radiator can be smaller, but its materials, coolant, and nearby equipment must withstand higher temperatures. A cooler radiator is safer for the materials, but requires a much larger surface area. An extremely powerful engine may require radiator wings larger than the spacecraft's main body. They would be thin, vulnerable to penetration by dust, and would need to remain properly oriented so that they did not absorb too much heat from the engine or a nearby star. This reveals an important engineering paradox. In the cold of space, a powerful spacecraft is difficult to operate not because it lacks heat, but because it cannot discard its excess heat quickly enough. Even matter-antimatter annihilation would not solve the problem completely. The energy released in the form of particles and gamma rays would be extremely difficult to direct, absorb, or convert into thrust without heating the spacecraft's structure. A highly concentrated energy source may make the cooling problem even more severe. If energy is supplied from a distance, the spacecraft carries less fuel but becomes dependent on precision. A sail millions of kilometers away occupies an extremely small angle in the sky. The laser beam must remain stable, compensate for disturbances, and continue striking the correct location while the vehicle accelerates. Every system also requires backups. A single reactor may be lighter, but one failure could end the mission. 2 reactors would be heavier but safer. Additional pipes, sensors, and controllers would increase the mass. Safety must be accelerated, along with everything else. With energies, this large navigational errors become serious. A very small misalignment in thrust, sustained for a long time, could cause the trajectory to miss its target by millions of kilometers. The engine must not only be powerful, it must remain precise for years, while its materials age and its sensors endure radiation. The spacecraft also cannot release all of its energy at once if passengers are aboard. Excessive acceleration pushes blood through the body and places heavy loads on tissues and structures. The energy must be released according to a schedule that the human body can tolerate. Suppose the engine produces an acceleration close to Earth's gravity. The passengers could feel as though they were standing on an ordinary floor. If that acceleration continued without interruption, the spacecraft's speed would increase by about 9.8 meters per second with every passing second. After one day, its velocity would have increased by approximately 850 kilometers per second, according to the initial classical calculation. After several months, relativity would become important. This may sound promising, but maintaining such acceleration for a large spacecraft over many months would require an enormous amount of power. The engine would need to operate continuously. The radiators would need to release heat continuously. A single prolonged malfunction could disrupt the entire acceleration and deceleration schedule. The energy source must also survive for the full lifetime of the mission. Nuclear fuel may contain great amounts of energy, but the materials inside a reactor are bombarded by neutrons, gradually changing their structure and becoming brittle. Magnets, insulation, pumps, and joints all age as well. It would not be enough to carry an engine designed to last 40 years and simply trust that it would continue operating exactly as it did on the first day. The spacecraft would need the ability to replace modules, recycle materials, and repair its energy systems while those systems were still in use. This is where an interstellar journey begins to resemble an industrial civilization more than a means of transportation. The spacecraft would not merely consume energy. It would need to manufacture components, inspect materials, replace equipment, and preserve the knowledge required to maintain its own machinery. A small robotic probe can accept a high level of risk. If it fails, the data is lost. A crewed spacecraft cannot be designed according to the same philosophy. Every critical system would require several layers of redundancy, increasing the vehicle's mass even further. Yet the greatest expenditure of energy during the journey would not produce a moment of victory. It would only bring the spacecraft to cruising speed. To truly arrive, all of that kinetic energy would have to be removed. The destination star grows brighter. The passengers may be able to observe its planetary system through telescopes. But unless the engines turn toward the direction of travel and begin braking, everything will pass by like scenery outside a window. The first half of the journey creates velocity. The second half must erase it. Waste heat can be expressed more concretely through the Stefan-Boltzmann law. An ideal black surface at about 300 Kelvin, close to room temperature, radiates only around 460 watts per square meter. Real materials radiate less, depending on their emissivity. If the spacecraft needed to discard 1 gigawatt of heat at close to room temperature, the ideal radiating area would need to exceed 2 million square meters if only one useful surface were counted. That would be an area equivalent to hundreds of soccer fields devoted solely to releasing heat. Raising the radiator temperature has a powerful effect because the radiated power increases with the fourth power of temperature. At 600 Kelvin, an ideal surface radiates more than 7,000 watts per square meter. The area required to reject 1 gigawatt would fall to about 140,000 square meters. But the pipes, pumps, and materials would have to operate at more than 300 degrees Celsius. Raising the temperature further would make the radiators smaller, but it would narrow the choice of materials and reduce the efficiency of certain equipment. Heat from the living areas could not simply be raised to thousands of degrees before being radiated into space. Heat pumps would be required, consuming more electricity and producing still more heat. This is why an extremely powerful energy source cannot simply be hidden inside the spacecraft's body. The cooling system may determine the vehicle's shape more than the engine itself. A high-power spacecraft might resemble a narrow central body passing through a forest of long radiator wings. Those wings could not be positioned directly behind the engine, where they would receive the hot exhaust. Nor could they face directly into the direction of travel, where dust would strike them. They would need a broad view of cold space and would have to avoid radiating heat toward one another. Near a star, incoming light reduces their ability to release heat. In interstellar space, the background sky is colder, but the radiators still emit energy only according to their own temperature. The phrase cold space does not mean that a hot object cools rapidly on its own. A vacuum removes convection, leaving radiation as the primary path for heat loss. The power system, engine, and radiators must therefore function as a single body. The greater the useful power, the greater the flow of waste heat. If the cooling system cannot keep up, the engines must reduce their output even if fuel remains available. A spacecraft may carry an energy source that appears powerful enough on paper, but be unable to use it continuously because it lacks sufficient radiating area. In that case, the true limit is not the amount of stored energy, but the rate at which entropy can be expelled. This also affects the acceleration strategy. Instead of operating continuously at maximum power, the spacecraft might work in cycles, firing its engines briefly and then waiting to cool. But each cooling period would extend the journey and make the acceleration uneven. If dust damaged the radiators, the spacecraft might still have engines, fuel, and electrical power, yet be forced to reduce nearly every activity. A small leak in a coolant line could limit the output of the entire vehicle. In space, the ability to generate energy is impressive. The ability to discard the portion that cannot be used is what determines how long a spacecraft can survive its own power. The human body does not feel constant velocity. A spacecraft may travel at tens of thousands of kilometers per second while remaining completely calm inside, as long as its speed and direction do not change suddenly. A cup resting on a table has no way of knowing how fast it is moving. Neither do the passengers. What they feel is acceleration. When the engines push the spacecraft, the floor presses against their feet and backs. When the vehicle changes direction, their bodies try to continue along the original path. Acceleration is the bridge between the energy of the engines and the limits of biology. Human beings can withstand large forces for brief periods if their bodies are positioned correctly. But forces acting from head to foot can pull blood away from the brain. Forces acting sideways or unevenly place stress on organs and tissues. A long journey would require acceleration that is moderate, stable, and interrupted by periods of rest. Acceleration equal to Earth's gravity is often used in examples because it would create a familiar sense of weight and is easy to visualize. But maintaining 1g continuously is not something current technology can do, and it cannot be treated as a guaranteed solution. It remains a useful thought experiment. If a spacecraft could accelerate at 1g for half the journey to Proxima Centauri, turn around, and then decelerate at 1g for the remaining half, relativity would produce a remarkable result. About 5.9 years would pass according to clocks on Earth, while the passengers would experience roughly 3.5 years. The maximum speed near the midpoint would be close to 95% of the speed of light. That is the beautiful side of the mathematics. The other side consists of energy, fuel, heat, and collisions at 0, 95°C, all far beyond present capabilities. The example does not prove that the journey would be easy. It shows that if high acceleration could be maintained for long enough, relativity really would shorten the time experienced by the passengers. But an important maneuver would have to occur halfway through the journey. The spacecraft would rotate by 180 degrees. Its engines would now point forward, even though the vehicle would still be traveling toward its destination. Thrust directed against the motion would gradually reduce the spacecraft's speed. Turning the spacecraft around would not send it back home. It would only change the direction of the force. A car can break through friction between its tires and the road. An interstellar spacecraft has no road. To stop, it must transfer momentum to expelled material, electromagnetic fields, light, or the surrounding environment. If the spacecraft used fuel carried on board, the braking fuel would already have needed to be accelerated throughout the first half of the journey. If it used a light sail driven by the destination star, the force would be weak and would depend on the star's brightness, the direction of approach, and the strength of the sail. If it used a magnetic sail to interact with stellar wind or plasma, the braking process could take a very long time and would need to begin from a great distance. Infrastructure at the destination would provide a better solution. A laser array could receive the spacecraft and slow it down. But no such structure would be waiting for the first mission. Before a bridge can be built, someone must cross the river without one. Deceleration would also affect the shielding. During acceleration, the nose of the spacecraft would face the direction of travel and carry thick protective layers. When the vehicle turned around to use its engines for braking, the structure would still need to ensure that the side facing the incoming stream of interstellar matter remained protected. The exposed engines, or wide radiator panels, could not simply be turned directly into the flow of dust. One design might place the engines behind a shield or provide protection at both ends. Another might redirect the thrust without rotating the entire spacecraft, but the system would become more complex. Every solution would add mass. Navigation during this stage would be especially difficult. The destination star would be moving. Its planets would be orbiting around it. The spacecraft would need to arrive at the correct location with the correct relative velocity. Entering a star system at excessive speed would not truly count as arriving. A planet would not be a stationary target either. To enter orbit, the spacecraft would need to encounter it at the correct point in its path, with a direction and velocity that allowed gravity to assist the approach, rather than turning it into another flyby. Data received on Earth would always describe the star system's past. During the journey, the spacecraft would need telescopes capable of measuring the positions of stars, planets, and smaller objects for itself. It would need to update its own map because it could not wait for instructions from home. At high velocity, even a small detection delay becomes a large distance. At 1 C, the spacecraft travels 30,000 kilometers every second. If the system takes 1 second to identify a hazard, calculate a response, and react, the vehicle will already have traveled nearly the circumference of Earth. Not every obstacle could be avoided. A dust grain may be too small to detect from far away. A larger object might be visible, but changing the direction of a massive spacecraft would require time. Strong sideways acceleration would also place heavy loads on the passengers and the structure. Interstellar navigation would therefore not resemble driving around obstacles on a road. Most safety would need to be built into the route and shielding before departure. The spacecraft would choose regions with lower matter density, observe the space ahead across several wavelengths, and avoid only objects large enough to be detected early. The second half of the journey is often neglected in imagination because acceleration feels like progress, while deceleration seems like going backward. But in terms of energy and time, braking may be just as important as departure. A spacecraft that achieves a record speed but cannot stop is only a scientific bullet. It may transmit data during a flyby, but it cannot establish a settlement, conduct a long-term survey, or deliver people to a planetary surface. The destination is therefore not simply a coordinate, it is a condition: the correct place, the correct time, the correct direction, and a low enough speed to remain there. As the engines point forward, the destination star continues to grow larger. The passengers may feel their weight shift direction, but the shielding must now face an environment that appears empty to the naked eye. At low velocity, a few atoms within every cubic centimeter have almost no meaning. At high velocity, they become a continuous beam of particles striking the front of the spacecraft. Even if the spacecraft reaches the correct star system, the destination may not resemble what Earth predicted. Telescopes often find planets by observing the way a star wobbles under their gravity or dims when they pass in front of it. From those effects, scientists infer orbital periods, approximate sizes, and minimum masses. But a small decrease in starlight does not reveal whether the surface contains oceans. Mass and radius do not automatically tell us whether the atmosphere is breathable or whether the magnetic field is strong enough. Two planets of similar size may be completely different. One may be dry rock, while another is covered by a thick, hot atmosphere. Atmospheric spectroscopy may search for water vapor, carbon dioxide, methane, and other molecules, but the signals are faint and can be affected by clouds, stellar activity, and the instruments themselves. Detecting a molecule is not simple proof of life. Many geological processes can produce the same substance. The destination star may also be highly active. Small red dwarfs live for extremely long periods, but they often produce powerful flares and release ultraviolet light and X-rays. A planet orbiting close enough to receive sufficient heat may experience intense radiation and become tidally locked, with the same side always facing the star. This would not necessarily make the planet uninhabitable. An atmosphere and oceans could transport heat. A magnetic field or thick layer of gas might protect the surface. But from Earth, many of these factors can only be estimated. The spacecraft would therefore depart for a place that was not fully understood. During several decades of flight, newer telescopes might improve the available data, but the vehicle's design decisions would already have been made. If the spacecraft carried people, this uncertainty would be difficult to accept. A reasonable strategy would be to send many robotic missions first. They could fly through the system, release instruments, and measure the atmosphere, magnetic field, radiation, and available materials. Automated infrastructure might produce fuel or build shelters, but the robot's data would take years to return to Earth. Once it arrived, humanity would need to design a crewed spacecraft and then spend additional decades reaching the destination. During that time, the star would not change significantly, but society and technology on Earth might be transformed. The destination might also be the space surrounding a planet rather than its surface. If the environment below proved dangerous, a community could live inside rotating stations and use asteroids or moons as sources of material. Reaching a planet would not necessarily mean landing immediately. An interstellar spacecraft should carry the ability to change its plans, but flexibility requires additional fuel, equipment, and knowledge. A design optimized for one specific planet would be lighter. A design capable of surviving many possible conditions would be heavier. This creates another feedback loop. Uncertain information requires backup systems. Backup systems increase mass. Greater mass makes the journey more difficult. Reducing those backups would require better observations before departure, but telescopes are also limited by distance. The obstacle, therefore, is not only reaching another world, it is knowing enough about that world before placing an entire community aboard a journey from which it may never return. There is no satellite navigation network between the stars. GPS works because many satellites broadcast precise timing signals, and users know their orbits around Earth. An interstellar spacecraft would leave that entire network behind very early in its journey. It could navigate using stars and pulsars. A pulsar is a rapidly rotating neutron star that sends beams of radiation sweeping through space like a lighthouse. Some pulsars pulse so regularly that they can serve as natural clocks. By measuring the arrival times of pulses from several directions, the spacecraft could estimate its position and correct its internal clocks. But pulsars are not perfect beacons. Their signals are weak. The interstellar medium alters their arrival times, and some pulsars display small irregularities. The spacecraft would need X-ray or radio detectors, maps of the sources, and continuously updated models. Ordinary stars could also provide guidance, but relativistic aberration would change their apparent positions as the spacecraft moved faster. Stellar distances are measured through parallax and proper motion. The computers would need to transform between maps created on Earth and the sky seen from a moving frame of reference. Atomic clocks aboard the spacecraft would maintain internal time. An error of 1/1000th of a second may sound tiny, but light travels nearly 30 centimeters during that interval. Across long measurements and many years, the clocks, sensors, and orbital models would all need to be calibrated. The spacecraft might carry several different types of atomic clocks. If one drifted, the others could detect it. Pulsars, stellar positions, and signals from Earth would provide external reference points, although every one of them would arrive from the past. As the spacecraft approached the destination system, planets and moons would become new landmarks. The vehicle would measure their spectra, angles, and motion to update its trajectory. A small error corrected early would require only weak thrust. The same error left until later would demand much more fuel. Interstellar navigation would therefore be continuous, not a matter of entering coordinates and allowing the spacecraft to travel in a straight line. Space contains stellar gravitational fields, moving targets, and accumulating errors. Every measurement carries uncertainty, and the computers must understand not only the best estimated value, but also how uncertain that value is. An autonomous vehicle would need to recognize when its map no longer matched reality. If the destination star had an unknown companion or a large planet altered the expected orbits, the spacecraft would have to update its model without waiting for Earth. Over a journey lasting decades, navigation software might be revised, but every change would need to be verified. A mistake in an update would not merely cause an application to stop working. It could make the spacecraft miss an entire star system after decades of travel. For this reason, the core calculations would need to exist in several independent versions, based on different principles and capable of checking one another. Navigation by stars, pulsars, inertial sensors, and direct observation of the destination would together form a safety network. Within an emptiness without road signs, the spacecraft would determine its location by measuring the moments when ancient pulses of light reached its detectors. It would find its way not through a living map, but by comparing the many clocks of the galaxy. The space between stars is often described as a vacuum, but only in a relative sense. It is far more rarefied than any ordinary vacuum chamber on Earth, yet it still contains hydrogen, helium, electrons, ions, weak magnetic fields, and dust. The density varies greatly from one region to another. Some areas contain only a fraction of an atom per cubic centimeter, while others are denser. A slowly moving spacecraft would pass through this environment without noticing much at all. But the energy of a collision depends on relative velocity. A proton at rest, relative to the interstellar medium, is nothing to fear. But when a spacecraft travels toward it at 1c, the proton strikes the nose of the vehicle with an energy of nearly 5 million electron volts in the spacecraft's frame of reference. That is the energy range of ionizing radiation. It no longer resembles a gas molecule gently touching a surface. At 5c, the energy carried by each proton rises into the hundreds of millions of electron volts. At velocities closer to the speed of light, the hydrogen atoms ahead behave like a beam of particles inside an accelerator. Space does not become denser. The spacecraft's velocity transforms the thin environment into radiation. From an outside perspective, the atoms are scattered far apart. From aboard the spacecraft, they arrive continuously from one direction, like an invisible rain. Each particle transfers energy to the surface, knocking electrons free, breaking chemical bonds, and producing heat. If the hydrogen remains electrically neutral, electric and magnetic fields cannot easily deflect it. Only after an atom has been ionized do its proton and electron respond strongly to those fields. A magnetic shield, therefore, cannot simply push everything aside as it often does in science fiction. A system might attempt to ionize the gas from a distance using lasers or powerful fields, then deflect the charged particles. But this would require energy, equipment, and a sufficiently large interaction region. Any neutral atoms that pass through would still strike the material. When a high-energy proton hits the shielding, it does not always stop within the outer layer. It may penetrate deeper, collide with atomic nuclei, and produce secondary particles. These new fragments carry energy in many directions, turning the armor itself into a source of radiation inside the spacecraft. This is why heavier materials are not always better. A thick metal plate may absorb many particles, but the heavy nuclei within the metal can also break apart into multiple fragments under bombardment. Hydrogen-rich materials, such as water or polyethylene, are often useful because they can slow protons while producing fewer heavy nuclear fragments. The spacecraft's nose might be built from several layers: an erosion-resistant layer, a particle-dispersing layer, a hydrogen-rich layer, and an empty gap before the living quarters. No layer would be perfect. The goal would be to reduce the energy step by step. The stream of hydrogen would also heat the front of the spacecraft. The thermal power would depend on the density of the surrounding medium, the frontal area, and the velocity. As the speed increased, not only would the spacecraft encounter more particles every second, but each particle would also carry more energy. The total effect would therefore rise very rapidly. A long, narrow spacecraft would have an advantage over a wide vehicle because it would present a smaller frontal area. The living quarters could be positioned behind the shield, like train cars sheltered behind a locomotive. Wide structures such as radiators, antennas, and sails would need to be arranged so that they did not directly face the incoming stream of particles. But the spacecraft would still need to observe what lay ahead. Telescopes, sensors, and radar would require a clear line of sight. Every opening in the shield would become a weak point. Optical instruments might be placed deep inside narrow tubes or use replaceable mirrors, allowing the outer surfaces to take the damage instead of the primary sensors. The incoming particles would also place an electrical charge on the spacecraft. Electrons and ions would not arrive in equal numbers or with equal energies. Ultraviolet radiation could also knock electrons away from the surface. If charge accumulated unevenly, electrical discharges could interfere with sensors or damage electronics. A large spacecraft would need to control the electrical potential between its different sections, distribute charge, and provide safe paths for discharge. Thin sails would be especially sensitive because even weak electrical forces could bend or rotate their broad surfaces. Interstellar magnetic fields are weak, but a charged object moving rapidly through a magnetic field still experiences a force. The effect might be extremely small from 1 second to the next, yet over many years it could accumulate into a deviation that required correction. Electronics inside the spacecraft would also suffer errors caused by high-energy particles. A proton passing through a microchip could change the state of a single bit. Computers would need error-correcting memory, multiple processors comparing their results, and backup copies of important data. If 3 computers performed the same calculation and one produced a different answer, the system could isolate it. Radiation, however, would not cause only immediate errors. It would gradually degrade transistors and sensors. Dead pixels might appear in a camera. Memory could become less reliable at retaining data. Insulating materials could grow brittle. The problem would not be one catastrophic failure, but billions of tiny injuries. When the spacecraft traveled more slowly, these effects would be weaker, but the journey would last longer. When it traveled faster, the period of exposure would be shorter, but every collision would be more powerful. No velocity eliminates both forms of risk. The important scientific point is that at 0, 1c, hydrogen is no longer merely a gas. In the spacecraft's frame of reference, each proton carries the energy of a radiation particle measuring several MeV. An environment that is almost empty has become a natural particle accelerator extending along the entire route. The spacecraft's nose quietly begins to warm. There is no sound of wind because there is not enough air to carry sound. Only the sensors record the continuous flow of energy. But hydrogen is still the lightest component. Within that rain of atoms, there may occasionally be dust grains carrying millions or billions of times more mass than a single proton. Relativistic velocity also changes the appearance of the sky. Because of the aberration of light, much of the light ahead appears to be compressed into a small region surrounding the direction of travel. The stars do not disappear, but their apparent positions shift toward the spacecraft's nose. Light arriving from ahead is also blue shifted, while light from behind is red shifted. At 0, 9, c, the forward Doppler factor is greater than 4. Visible blue light may shift into the ultraviolet, while ultraviolet radiation can move into still higher energy ranges. The sky ahead is not merely brighter in certain directions. Its radiation spectrum also changes. The cosmic microwave background currently has a temperature of about 2.7 Kelvin and lies within the microwave region of the spectrum. At velocities extremely close to the speed of light, the radiation arriving from ahead gains energy. Only at extraordinarily large Lorentz factors would it become a hazard comparable to X-rays. But the principle shows that no background radiation remains unchanged when the spacecraft enters a different frame of reference. Similarly, light from the destination star gains energy as the spacecraft rushes toward it. The optical systems and shielding would need to account for photons as well as particles of matter. A filter designed for visible light while at rest might receive ultraviolet radiation once the spacecraft was moving fast enough. Behind the spacecraft, signals from Earth would be redshifted and would arrive at a slower rate. This could create the impression that home was growing dimmer and slower, not because time there was truly passing more slowly, but because of the way light waves reached an observer moving away. These effects would also make navigation more difficult. Star maps would need to be transformed according to the spacecraft's velocity. A computer could not directly compare the sky observed at 0.9c with a map created on Earth. It would have to correct for aberration, Doppler shifts, and light travel time. A fast spacecraft would therefore see a universe with a different apparent geometry. The region ahead would be compressed and shifted toward higher energies, while the region behind would be stretched and reddened. Space itself would not change locally, but the measurements made by a moving observer would change profoundly. An interstellar dust grain may be smaller than the human eye can see. It may be a fragment of silicate, carbon, metal, or ice, drifting through the darkness since long before the spacecraft was built. At low velocity, such a grain might do little more than scratch the surface. At 0.1c, kinetic energy completely changes the meaning of size. A particle with a mass of 1 microgram, or 1/1,000,000th of a gram, carries about 450,000 joules at 0.1c. That is enough energy to produce a small explosion concentrated at an extremely narrow point. A particle with a mass of 1 milligram, still only a tiny fragment of matter, carries about 450 million joules at the same velocity. That energy is equivalent to more than 100 kilograms of TNT, although the exact damage would depend on the material, the angle of impact, and the way the energy was dispersed. This does not mean that every dust grain would destroy the spacecraft. Most particles would be much smaller, and the density of dust in space is low. But it shows why dust cannot be treated as merely a problem of keeping the surface clean. The collision would occur so quickly that the material would not have time to transfer heat in the ordinary way. The dust grain and the section of shielding at the point of contact would be compressed, heated, ionized, and possibly transformed into plasma. A small crater would form. Shock waves would spread through the material. The danger would not come only from the external object. The back surface of the shield could break apart into high-speed fragments. A single impact could create a cloud containing the original dust, material from the shielding, and plasma, all continuing inward. For this reason, effective armor is often not a single solid block. A multi-layer design places a thin plate at the front, an empty gap behind it, and the main protective layer farther back. The first plate breaks the particle into a cloud. Within the gap, that cloud expands. By the time it reaches the second layer, its energy is distributed across a larger area. This principle has already been used to protect spacecraft from orbital debris traveling at much lower velocities. For interstellar travel, the energies would be far greater, and the shielding would need to be thicker, more widely separated, or replaceable. The first plate would be a sacrificial component. It would not be designed to remain intact. Its purpose would be to erode and break apart in place of the living quarters. After many years, the shield would become a physical record of every collision encountered along the route. Water or ice could be placed near the front. It could serve both as stored material and as a way to absorb energy and slow fragments. Ice might be replenished using recycled water if the system allowed it. But every kilogram of water would also have to be accelerated, so thicker protection would make the energy problem more difficult. Another idea would be to release a cloud of small particles or a thin layer of material ahead of the spacecraft. These particles would collide with incoming dust first, ionizing it or breaking it into a cloud that magnetic fields and shielding could handle more easily. But the protective screen would also need to be maintained, guided, and prevented from becoming a hazard to the vehicle itself. Forward-pointing lasers might detect or vaporize some larger particles, but very small dust grains reflect too little light to be seen from a safe distance. At 1 million kilometers corresponds to only about 33 seconds of travel. An object detected at what sounds like an enormous distance could still arrive very quickly. The spacecraft could not change direction instantly either. A vehicle weighing thousands of tons could not dodge individual grains the way an airplane avoids birds. Sideways acceleration would place loads on the passengers and the structure, while the dust would be far too abundant and too small to map particle by particle. A realistic strategy would be to select a route through regions of lower density, use telescopes to detect larger objects, and design the spacecraft to survive countless minor impacts. Evasive maneuvers would be reserved for hazards that were large enough, bright enough, and detected early enough. Optical surfaces would be especially vulnerable. A mirror needs to lose only a very small amount of smoothness before its quality begins to decline. Windows could become cloudy after accumulating millions of microscopic craters. Forward-facing sensors would need protective covers, replaceable mirrors, or indirect lines of sight. Radiators would also be fragile. They would need to be broad enough to release heat, but a larger surface would have a greater chance of being punctured. Coolant inside their pipes could leak away. The radiator system would therefore need to be divided into many independent circuits, so that one puncture would not disable the entire cooling system. Maintenance robots might crawl along the structure, measuring shield thickness through ultrasound or other methods, replacing panels and sealing cracks. But robots could not work freely on the front surface, while the spacecraft was receiving a stream of high-energy particles. The design would need to allow repairs from behind or permit damaged sections to be rotated into protected areas. The materials would also experience thermal fatigue. An impact point would heat up and then cool down. Repeated small cycles would create fractures. The shield might appear intact while its internal structure had already weakened. Monitoring systems would need to detect changes in vibration and sound transmission before the fractures could spread. Objects larger than dust grains would be far rarer, but their consequences would be much more severe. A pebble or fragment of ice striking at 1C would exceed the capabilities of ordinary shielding. Because larger objects are easier to detect from a distance, the chance of seeing them early would be better. But no survey could guarantee knowledge of every dark object between the stars. This creates a practical limit on velocity. The higher the speed, the heavier the shielding must become, and the greater the required detection distance. Beyond a certain point, the benefit of shortening the journey would be consumed by the mass of the protection and by risks that could no longer be managed. In stories about interstellar spacecraft, the armor is often treated as a permanent structure. In reality, it would behave more like fuel, a resource gradually consumed. Every impact would remove a little thickness, smoothness, or strength. The maintenance displays might show not only the distance remaining, but also the remaining shield budget. If erosion occurred faster than expected, the spacecraft might need to reduce its speed, change its route, or move stored material toward the front. A tiny flash appears on the nose of the spacecraft and then disappears. Nothing is heard inside the living quarters. But a dust grain has been transformed into plasma. The shield has lost more material, and a maintenance robot has recorded a new indentation. Armor may withstand the things that leave craters. The next danger does not need to dent the surface. It can pass through material, move through the human body, and leave damage at the molecular level. On the ground, human beings live beneath two major layers of protection: the atmosphere and Earth's magnetic field. The atmosphere absorbs much of the ultraviolet light and X-rays that arrive from space, while also creating chains of interactions that reduce the energy of incoming particles. The magnetic field deflects some of the charged particles released by the sunday. Beyond those protective layers, radiation comes from many sources. The sun produces the solar wind and occasionally releases bursts of high-energy protons. Galactic cosmic rays arrive from beyond the solar system and consist largely of protons and atomic nuclei accelerated by powerful events such as supernova remnants. The spacecraft itself may produce radiation through its reactors, while collisions with interstellar hydrogen create additional secondary particles. Electromagnetic radiation and particle radiation are not the same. X-rays and gamma rays are high-energy photons. Cosmic rays are mostly particles of matter moving at extremely high speeds. Both can ionize atoms, but they require different forms of shielding. A high-energy proton can pass through many layers of material. When it strikes an atomic nucleus, it may produce neutrons and secondary nuclear fragments. For this reason, adding more heavy metal does not always make the interior safer. Water, plastic, and other hydrogen-rich materials can slow certain particles more effectively for their mass, while producing fewer heavy nuclear fragments. This is why water tanks, food supplies, and even processed waste could be arranged around sleeping areas. No material can block every form of radiation. The goal is to reduce the dose, distribute protection wisely, and limit the time people spend in areas with less shielding. A storm shelter could be located deep within the spacecraft, surrounded by water and supplies. When sensors detected an intense burst of particles from a star, the passengers could remain there for several hours or days. There would be no wind and no thunder. The storm would appear only on the monitors as a rising count of incoming particles. Galactic cosmic rays, however, are always present. No one could spend an entire lifetime inside a small shelter. The spacecraft's entire architecture would need to reduce long-term exposure. Sleeping quarters would require strong protection because people spend nearly 1/3 of their lives there. Work areas close to the outer hull would be used only when necessary. Robots would handle external inspections. Water and cargo could be moved to different locations according to radiation levels. Using supplies as shielding creates a changing problem. Food is consumed, fuel levels fall, and water moves between tanks. The protective arrangement in the present would not have the same shape 10 years later. Mass management software would need to ensure that the living areas did not lose shielding as supplies changed. Radiation affects DNA either by directly ionizing molecules or by creating highly reactive chemical radicals. The body can repair much of this damage. A single particle passing through tissue does not mean that illness will appear immediately. The danger comes from probability and accumulation over time. Beyond the risk of cancer, radiation can affect blood vessels, the nervous system, the eyes, and other tissues. The severity depends on the type of particle, its energy, a person's age and biology, and the length of exposure. Almost no data exists on human beings living for decades beyond Earth's magnetosphere. This is a major uncertainty. We have data from astronauts, animal experiments, and scientific models, but no human community has lived across multiple generations within the radiation environment of interplanetary or interstellar space. Electronic systems would also receive an accumulated dose. A single particle could flip a bit in memory. Many particles could gradually alter the behavior of transistors. Cameras might develop false bright spots. A sensor could begin producing inaccurate readings while continuing to operate, which may be more dangerous than a device that stops working completely. Critical systems would require several layers of verification. Data would be stored in multiple locations. Memory would be scanned and corrected for errors. Computers would use radiation-resistant architectures, even though these are often slower and consume more power than commercial electronics. The spacecraft's energy source would create its own shielding problem. A reactor should be placed far from the living areas. perhaps at the end of a long structural boom. Distance would reduce the intensity of the radiation, but a longer boom would add mass and introduce more potential failure points. Shielding could be concentrated in one direction, using fuel or water positioned between the reactor and the crew. If the spacecraft rotated to produce artificial gravity, the radiation layout would become even more complicated. The inhabited ring would move, while the reactors and engines might remain along the central axis. Electricity, coolant, and data would need to pass through rotating joints while the radiation sources remained far away. Travel speed affects the problem in two opposing ways. A faster journey reduces the number of years spent exposed to cosmic rays, but causes the hydrogen ahead of the spacecraft to produce more powerful radiation. Slower travel reduces the energy of those collisions but increases the accumulated dose over time. An optimal velocity may exist for a particular spacecraft design where the combined risks from travel time and high-speed impacts reach their lowest level. But that velocity would depend on the density of the surrounding medium, the shielding, the available energy, and the health of the passengers. There is no single number that applies to every spacecraft. Radiation does not create one clearly defined day when the vehicle changes from safe to dangerous. It is more like aging. One cell is damaged. One sensor loses a little sensitivity. One polymer becomes slightly more brittle. Each change may seem insignificant on its own, but together they accumulate over many years. Protection, therefore, is not merely a layer of material. It includes location, time, architecture, medical monitoring, equipment repair, and operational decisions. Inside the sleeping quarters, water tanks form thick walls. Outside, detectors record each particle that passes through. Some stop within the outer hull. Some create secondary particles. Others reach sensors located deep inside the vehicle. The spacecraft cannot eliminate radiation completely. It can only reduce the energy, reduce the exposure time, and ensure that small injuries do not accumulate into a system-wide failure. To accomplish this, every resource must serve several purposes. Water is both something to drink and a radiation shield. Food provides nourishment while also absorbing particles. Waste must be processed, yet it cannot simply be discarded whenever convenient. From this point onward, the spacecraft is no longer a machine supplied from the outside. It must reuse matter almost indefinitely, even though no real system can operate without some losses. Passive shielding is not the only possibility. Powerful magnetic fields could deflect protons and ions, much as Earth's magnetic field deflects part of the solar wind. A large superconducting coil could create an artificial magnetic bubble around the spacecraft. But the more energetic a particle becomes, the larger its path curves within a magnetic field. Deflecting a powerful cosmic ray proton across a short distance would require either an enormously strong magnetic field or an enormous system. The magnets producing that field would also have mass, require cooling, and store great amounts of energy. If a superconducting coil lost its superconducting state, the stored magnetic energy would need to be released safely. A failure could heat the coil and trigger damage that spread through the system. Active shielding would therefore require redundancy, just like every other critical system. Electric fields could deflect charged particles, but extremely high voltages in a vacuum would create risks of electrical discharge, electron attraction, and unstable charge accumulation. Neutral particles and photons would not be stopped in this way. A hybrid system might use magnetic fields to reduce the number of charged particles and hydrogen-rich materials to absorb what remained. The physical shielding could be placed some distance from the living quarters, allowing secondary particles to spread out before reaching the crew. Sometimes, however, the best protection is simply reducing the exposure time. A shorter mission receives a lower accumulated dose, but shortening the mission requires higher velocity, which increases the radiation coming from ahead. This is one of the clearest examples of why no single solution is sufficient. Medicine could help through DNA monitoring, early detection, and treatment, but it should not be treated as a shield. Repairing damage after it occurs is not equivalent to preventing it. Across multiple generations, the effects on reproductive cells and human development would need to be understood far more deeply. Radiation would also alter microorganisms and crops. Most mutations are neutral or harmful, although some occasionally create new variations. Within a small ecosystem, a change in the microbial population could spread quickly. Seed banks and biological backup samples would need stronger protection than the areas used for everyday activity. The safest location might be close to the spacecraft's center of mass, surrounded by water, growing soil, and stores of raw material. The architecture of the vehicle would therefore resemble an onion with many layers, machinery and supplies on the outside, with people and biological archives protected deep within. An adult uses hundreds of kilograms of water each year when drinking, food preparation, and hygiene are all included. On Earth, most of that water enters natural systems or vast networks of infrastructure. Aboard an interstellar spacecraft, nearly every drop would need to be recovered. Water vapor in exhaled breath would condense on heat exchangers. Moisture from sweat would be removed from the air. Wastewater would pass through mechanical, chemical, and biological filtration. After many stages, it would return to the clean water tanks. A system might recover most of the water, but most does not mean forever. Imagine a community of 100 people permanently losing only 10 grams of water per person each day through leaks, materials, exhaust, or waste that could not be processed. The total loss would be 1 kilogram per day, more than 360 kilograms per year, and over 18 metric tons after 50 years. 10 grams would be almost unnoticeable in a single day. Across half a century, it would become a mass that had to be carried from the beginning or recovered from another source. The same problem applies to oxygen, nitrogen, carbon, phosphorus, and trace elements. Matter does not disappear, but it can become trapped inside filters, react into compounds that are difficult to reuse, adhere to pipe walls, or escape through leaks. A real closed system is not a perfect circle. It is a slowly leaking spiral. The engineering challenge is to make the loss rate small enough and carry reserves large enough. Air would also need to be recycled continuously. Human beings inhale oxygen and exhale carbon dioxide. The system could use chemical reactions, water electrolysis, and plants to restore oxygen. But maintaining the correct gas ratios would be only the beginning. Plastics, adhesives, electrical equipment, and cleaning agents all release small quantities of compounds. On Earth, these substances are diluted by large spaces and ventilation. Aboard the spacecraft, they would keep circulating. A compound present at an insignificant concentration today might accumulate over many years. Sensors would need to monitor a wide range of substances, but sensors would also age. A device measuring 1% incorrectly might not trigger an immediate alarm, yet it could cause the system to make incorrect adjustments over a long period. Important measurements would therefore require several independent instruments and regular calibration. Filters would become clogged with dust, fabric fibers, and skin cells. Valves would jam, seals would lose elasticity, pipes would corrode, pumps would begin vibrating in unfamiliar ways. An enclosed world could depend on a component so small that it would be difficult to believe. If a city's water pump failed, a repair team could order replacement parts. On an interstellar spacecraft, the nearest factory would be several light years away. Every failure would have to be solved using only what was already on board. Carrying one spare copy of every component would not be practical. No one could know exactly which part would fail 30 years later. Too many backups would make the spacecraft heavy. Too few would make the system fragile. The solution would be to carry raw materials and manufacturing capability. Metal printers, machining equipment, recycling furnaces, and measuring tools could transform old material into new parts. A failed valve could be removed, sorted, melted down, or machined into a different component. But the manufacturing equipment would also fail. Printer heads would wear down. Cutting tools would become dull. Sensors would drift out of calibration. The spacecraft would need the ability to repair the machines used to repair all the other machines. In the end, it would still require simple tools, knowledge of materials, and human skill. This is a limit that is often overlooked. Self-sufficiency requires more than a warehouse of spare parts. It requires an industrial chain. Manufacturing a bearing requires the correct material, precision, lubrication, and measuring equipment. Replacing an electronic chip requires either semiconductor manufacturing capability or an architecture based on standardized modules that can be reconfigured. It would not be easy to compress all of Earth's industry into one spacecraft. Many modern products depend on supply chains extending across dozens of countries and thousands of factories. An interstellar community would need to simplify its designs, standardize components, and prioritize systems that could be repaired using common tools. Food would make the problem even more complicated. Carrying several years of food would already require great mass. Carrying enough for many generations would be nearly impossible. The spacecraft would need to grow plants, cultivate microorganisms, or produce food through other methods. Plants use light, water, carbon dioxide, and nutrients. They produce oxygen and food while also bringing green life into the habitat. But plants are not free machines. Lights require electricity. Electricity becomes heat. Water must be pumped. Nutrients must remain balanced. Fungi and bacteria may spread through the root systems. A small garden does not automatically become a biosphere. On Earth, soil contains networks of organisms supported by climate and vast cycles of matter. Aboard the spacecraft, every link would need to be selected and monitored. If the community grew only a few highly efficient crop varieties, the system would become vulnerable to disease. If it grew too many varieties, the required area and energy would increase. If it depended too heavily on a single harvest, a failure in lighting or nutrients could threaten the entire food supply. The community would need several layers of support: stored food, crops, microorganisms capable of producing protein or nutrients, and the ability to adjust diets when one part of the system failed. Waste could not simply be thrown outside. It would contain water and elements needed by the plants. Organic material would need to be broken down, but the process would have to control pathogens and toxic substances. A small ecosystem would lose balance more easily than Earth's biosphere because it would have no oceans or vast areas of soil to absorb mistakes. Microorganisms would be both allies and risks. They would live on the skin, inside the digestive system, within pipes, and inside filters. The spacecraft could not be completely sterilized while keeping human beings healthy. The goal would be to manage its microbial communities, not eliminate them. A bacterial film inside a pipe could restrict flow, corrode material, or alter water quality. A species that remained harmless on Earth might grow excessively inside a closed environment. The system would need to collect samples, analyze them, and maintain backup cultures. Across many decades, the ecosystem and its human inhabitants would change together. Microorganisms evolve quickly. Plants would be selectively bred for the spacecraft's environment. The community would adjust its diet and habits. The vehicle would gradually become a biological environment of its own. Stability would not mean keeping everything unchanged. It would mean being able to recover after a disturbance. If one harvest failed, another source would compensate. If a filter stopped working, a backup path would take over. If one microorganism became too abundant, the system would respond before the entire cycle collapsed. A machine has a finite operating life. A sustainable ecosystem survives through the continuous replacement of its parts. Cells die, organisms are born, and matter circulates. An interstellar spacecraft would need both qualities: the precision of machinery and the ability of biology to repair and renew itself. After several generations, most of the original components might have been replaced. The water would have passed through bodies and filters countless times. The carbon atoms in today's meal may once have been present in the breath of someone who died many years earlier. The spacecraft would not carry a supply of matter meant to be used only once. It would carry a finite amount of matter that had to tell the same story again and again in many different forms. But even if air, water, and food remained stable, the human body evolved under Earth's gravity. A habitat that was chemically perfect would not necessarily be mechanically perfect. Even a system that retained every atom could not recycle matter without consuming energy. This is a limit imposed by thermodynamics. Matter may be recovered, but through use it becomes mixed, contaminated, and dispersed. Separating it again requires work, equipment, and time. A glass of clean water and a glass containing hundreds of compounds may contain the same number of water molecules, but they do not have the same practical value. The filtration system must create order from a mixture. That process produces heat and gradually degrades the filtering materials. It is impossible to build a perfect recycling machine that runs forever using only its own waste. It requires a source of high-quality energy and a place to release low-quality heat. A spacecraft closed to matter must remain open to energy, receiving power from a reactor or from light, then radiating heat into space. This is the difference between the cycling of matter and the flow of energy. Atoms can move in circles. Useful energy moves in one direction, from a concentrated source toward dispersed heat. Earth's ecosystem operates in a similar way. The sun supplies energy, living organisms use it, and Earth eventually radiates heat back into space. A spacecraft would not create an ecosystem simply by sealing its doors more tightly. It would create one by keeping matter within repeating cycles while allowing energy to pass through. Trace elements would present challenges of their own. Plants require iron, zinc, molybdenum, and many other substances in small amounts. If one element became trapped in residue or a filter, the plants could suffer a deficiency even if the total mass aboard the spacecraft had barely changed. The system would need to monitor not only water and carbon, but dozens of elements. A quantity of only a few grams might determine the success of an entire harvest. Inside a closed environment, the rarest resource may be the substance required in the smallest amount. Life would also create new molecules. Microorganisms release compounds, plastics degrade, and medicines and hormones enter the wastewater. The concentration of each substance might be extremely low, but thousands of compounds would exist together. The filtration system could not be designed only for the substances known on the day of departure. The spacecraft would need broad chemical analysis capabilities, the ability to update its procedures, and the means to manufacture new filtering materials. A sustainable artificial ecosystem would be a laboratory that never stopped operating. In microgravity, the body does not have to support its weight the way it does on the ground. The muscles in the legs, back, and abdomen do less work. The bones bear less load. The heart does not need to pump blood against gravity in the same way. The body adapts, but that adaptation is suited to a weightless environment. It is not necessarily suited to returning to a planet. In some weight-bearing regions of the skeleton, mineral density can decline significantly during long missions if no countermeasures are used. Muscles weaken, blood volume changes, fluids shift toward the upper body, contributing to a fuller-looking face and thinner legs. The balance system in the inner ear must relearn how to function when there is no clear downward direction. Some astronauts experience changes in vision. The immune system, metabolism, and sleep are also affected by the environment, radiation, and work schedules. Exercise helps reduce many of these effects. Treadmills use restraints to hold the body down, while stationary bicycles and resistance devices force the muscles and bones to work. But exercise requires several hours. The equipment occupies space, produces heat, and can fail. 1 hour of exercise cannot fully replace 24 hours of living under gravity. Processes such as fluid distribution and the continuous mechanical signals received by bones remain different. An appealing solution is to create artificial gravity through rotation. When a habitat rotates, its outer wall continually forces people to move along a circular path. This feels like an outward force and can create a floor along the outer wall. The level of gravity depends on the radius and the rotation rate. This is where the numbers become memorable. If the structure rotates only once per minute, producing close to 1 g at the outer wall would require a radius of roughly 900 meters. The diameter would be nearly 2 kilometers, comparable to a small city-sized structure. If the speed increased to 2 rotations per minute, the required radius would fall to about 220 meters. At 4 rotations per minute, it would shrink to approximately 56 meters. But faster rotation causes movements of the head and body to produce stronger Coriolis effects, making dizziness and disorientation more likely. A small ring would also create a difference in gravity between the head and feet. The feet would be farther from the center and would experience a stronger force. Inside a very small structure, a person might feel that their feet were heavy while their head was noticeably lighter. A large ring rotating slowly would provide a more comfortable environment, but it would require more mass and greater structural strength. The material in the ring would remain under constant tension. Over several decades, fatigue cracks could grow. The joints would need to be inspected and replaced. If the entire spacecraft rotated, aiming the engines, antennas, and radiators would become difficult. If only the living section rotated, connections would be required between the rotating and non-rotating sections. Electricity, water, air, and data would have to pass through those joints for decades without leaking or failing. Another design could use 2 habitats connected by a long cable, rotating around a shared center. This would create a large radius with less structural material, but the cable would remain under continuous tension, and the system would need to control oscillations. If the mass of one habitat changed because water or cargo was moved, the rotational balance would also change. Artificial gravity would also conflict with the acceleration phase. When the engines produced acceleration along the spacecraft's axis, the downward direction created by thrust and the downward direction created by rotation could combine into a tilted vector. The spacecraft would need floors and living spaces designed to function under several gravity configurations. We do not yet know the minimum level of gravity required to maintain long-term health. Martian gravity, about 38% of Earth's, may be sufficient for some biological functions, but not for others. There is no multi-generational evidence from which to draw a firm conclusion. This is especially important for children. Adults boarding the spacecraft would already have developed under 1 g. Their bones, muscles, and nervous systems would carry that history. A child born in low gravity would develop within the new environment from the beginning. We do not know how human pregnancy, organ development, bone growth, and the balance system would progress through the entire process under microgravity or low artificial gravity. Animal studies provide clues, but they cannot replace long-term research involving human beings. A person born under 3 g might be completely healthy in that environment, but face serious difficulty upon reaching a planet with 1 g. Their body would not be weak in a general sense. It would be optimized for a different world. If the spacecraft maintained 1 g across many generations, while the destination had only 4 g, the community would then need to adapt in the opposite direction. It would be impossible to choose the perfect onboard environment without knowing the destination's conditions with certainty. Gravity would also affect the design of the ecosystem. Water flows differently, plant roots grow differently, waste settles differently, and flames behave differently in microgravity. A rotating habitat would make these systems more familiar, but it would also introduce gradients and unusual motion. The human body requires more than the correct composition of air. It needs mechanical forces, movement, light, and biological rhythms. Life is shaped by physics as well as chemistry. A large ring rotates slowly around the spacecraft's central axis. Inside, children may run across the curved floor without feeling its curvature. Water remains inside a cup. Plants grow toward the light, while their roots follow the effective force. But beyond the ring is vacuum. The gravity beneath their feet comes from a machine. If the ring stops, the floor loses its weight. This would make everyone understand an ordinary truth about their world. It is not held together by a planet. It is held together by bearings, control motors, load-bearing materials, and the people who know how to repair them. Isolation aboard an interstellar spacecraft would be unlike any form of isolation experienced on Earth. People living at polar stations, aboard submarines, or inside simulated habitats still know that a larger world exists beyond them and that their missions will eventually end. On a generation ship, metal corridors may be the entire world for a person's whole life. There would be no outside space for a walk, no other city to move to, no entirely new group of people to replace the existing community. Every person would depend on others they might not even like, because maintaining air, water, and energy would require cooperation. Conflict would not necessarily erupt into violence. The more realistic danger would be the accumulation of small disagreements. An impatient remark, a division of labor perceived as unfair, or a repeated noise from the neighboring cabin. On Earth, distance can soften these problems. Aboard the spacecraft, people would continue meeting one another for years. The sound of machinery would always be present. Fans, pumps, the rotating habitat, and cooling systems would create a continuous background hum. Complete silence might be frightening because it could mean that a piece of equipment had stopped. An environment with very little natural change would cause time to lose its landmarks. There would be no real seasons, rain, or natural sunset. Software would control the cycle of day and night. If daily routines became too repetitive, one week could begin to blend into the next. The biological clock requires a clear cycle of light. Morning illumination would need to increase gradually. In the evening, blue light could be reduced, and the temperature might fall slightly. Sleep would not be merely a matter of comfort. Fatigue increases technical mistakes and reduces the ability to resolve disagreements. Private space would also be a form of safety equipment. A small personal cabin would allow someone to close the door, control the lighting, and avoid constantly displaying emotions in front of others. In a design optimized to reduce mass, private floor space might appear wasteful, but removing it could create a much greater psychological cost. Data privacy would matter as well. The spacecraft systems might monitor heart rate, sleep, radiation exposure, and location to maintain safety. But if every conversation and behavior were observed, the community could lose trust. Clear rules would be needed to determine who could view each type of data and under what circumstances. The garden would have value far beyond food production. It would be a place where change was not created entirely by a screen. A new leaf, a blooming flower, or ripening fruit would mark the passage of time. The smell of plants and the humidity of the air would feel different from metal. Art, music, and rituals would not be decorations either. They would help the community create shared memories. The day an engine was replaced, the first clear view of the destination planet, or the anniversary of departure might become a festival. But an overly rigid schedule would turn people into components of a machine. They would need time that did not serve the mission. A society could not survive across many generations if every source of joy were postponed until arrival. Important work would require cross-checking. No person can remain accurate at all times. The system should allow someone to say they are too tired to perform a non-urgent task. This would require several people to be trained for the same role, increasing the need for education, but reducing dependence on any single individual. Leadership aboard the spacecraft would raise difficult questions. During a loss of pressure emergency, someone would need to make rapid decisions. During ordinary life, emergency authority should not become permanent authority. A commander could grow old, become ill, or lose the ability to serve, the community would need mechanisms for transferring power, reviewing decisions, and limiting authority. Rules written on Earth before departure might no longer be suitable 50 years later. The law would need to be stable enough to protect basic rights while remaining flexible enough to adapt. The system could not exile anyone into the vacuum. Justice would need to focus on restoring the ability to cooperate, because both the person who caused harm and the person who was harmed would continue living aboard the same spacecraft. Scarcity can easily be used to justify control. Water, energy, and space would truly be limited, but not every restriction placed on individuals would be necessary for survival. The community would have to distinguish between genuine survival requirements and habits of power. Psychological support could not depend on Earth. When someone needed help, a response from home might take years. The spacecraft would need its own expertise, culture of care, and internal tools. Personal messages would carry a particular kind of sadness. The recipient would watch a face recorded many years earlier. The person in the video might have grown old or died by the current moment, but the image would remain young. Every message would be an encounter with the past. Isolation experiments could help prepare the crew, but they could not reproduce the knowledge that there was no route home. A person at a research station knows that an aircraft may arrive after several months. A person between the stars knows that no vehicle could reach them within their lifetime. The deepest danger would not be the certainty that the community would become violent. It would be the loss of meaning. If the people aboard the spacecraft saw themselves only as caretakers of a mission created by those who had already died, they might no longer agree to continue it. A perfectly functioning engine could not answer the question of why the destination must still be reached. If one generation wanted to change course, remain aboard the spacecraft permanently, or refuse to land, instructions from Earth could not be imposed immediately. Social sustainability would therefore be as important as technical sustainability. The spacecraft would need the ability to repair its laws just as it repaired its machinery, without treating human beings like replaceable components. A shared meal begins inside the dining area. Leaves move gently beneath the artificial airflow in the garden. In the corridor, the steady sound of the pumps continues. Small things like these maintain the rhythm of life. But if the journey lasts longer than a human lifetime, the final authority to decide its future will eventually pass to people who never chose to board the spacecraft. A generation ship is not simply a spacecraft undertaking a very long flight. It is a place where many people are born, live, and die before the vehicle reaches its destination. The departing generation remembers Earth. The next generation remembers stories about Earth. After several generations, the planet becomes part of history rather than personal memory. Inside a classroom, children may watch videos of rain falling. They understand from books that water descends from clouds to the ground, but they have never felt drops falling freely from the sky. They know that an ocean is larger than every compartment aboard the spacecraft, yet their direct experience of water consists only of storage tanks, pipes, and growing areas. That difference changes the way they understand home. To those who departed, the spacecraft is a vehicle. To those born aboard it, this is the place that contains their families, graves, schools, and history. It does not lie between two homes. It is the only home they have ever known. Before such a society could exist, the problem of population would have to be solved. A community that is too small could lose genetic diversity, lack essential skills, and become highly vulnerable to accidents. A community that is too large could exceed the available food, energy, and living space. There is no single minimum population that science can guarantee would be sufficient. The result would depend on the duration of the journey, birth rates, family structure, medical care, stored biological material, the diversity of the original population, and the way the community managed genetic drift. A group of several hundred people might be supported by banks of embryos, eggs, sperm, or cells collected from a far larger number of people on Earth. This could reduce the need to carry an enormous population from the beginning, but it would create dependence on cryogenic storage, medical equipment, and ethical decisions extending across many generations. The biological archive would need to survive longer than the people who created it. If the cooling system failed, part of the genetic diversity could be lost. If records of biological origins could no longer be read, the community would struggle to manage family relationships and hereditary diseases. Genetics would be only part of the problem. Pregnancy and childhood development under artificial or reduced gravity are not yet fully understood. Radiation could affect reproductive cells and developing tissue. The medical system would need to follow many generations without access to an outside hospital. The population would also need to remain within the ecological capacity of the spacecraft. Every person requires energy, water, oxygen, food growing area, and waste processing capacity. A small change in the birth rate, sustained over many years, could cause the population to exceed its limits or fall below the number needed to maintain essential work. But human beings cannot be managed like livestock simply to make the numbers fit a spreadsheet. The freedom to make decisions about family and one's own body is central to human dignity. A coercive system might keep population figures stable while destroying trust and social health. There is no easy solution. Personal freedom aboard the spacecraft would always interact with shared resources. The community would need mechanisms based on consent, care, and fair distribution rather than assuming that the mission justified control over every private decision. Knowledge would be the second resource that had to survive across generations. The spacecraft might depart with a digital library containing much of humanity's knowledge, but data does not make itself immortal. Memory systems would suffer radiation damage, bit errors, and aging. Software formats would become obsolete. A file that remained physically intact but could no longer be decoded would be like a book written in a language no one could read. Data would therefore need to be copied regularly onto new storage devices, checked using error correction codes, and preserved in several formats. Foundational knowledge should also exist in simple physical form, from diagrams of life support systems to basic principles of mathematics, physics, and medicine. But documentation is not the same as skill. A manual can describe the sound of a failing bearing, but someone who has never heard it may struggle to recognize it. An agricultural textbook cannot replace the experience of looking at the color of a leaf and understanding which mineral its roots may be lacking. Rare skills could easily disappear if only one person possessed them. Every critical task would need to be learned by several people, including younger members working alongside older experts before that knowledge was lost. Education would therefore become part of the life support system. A society aboard the spacecraft could not treat learning as a stage reserved only for children. Every generation would need to train the people who would eventually replace it. Some skills might not be used for decades. Landing techniques, planetary soil treatment, or the construction of outdoor shelters might become necessary only near the destination. Without regular simulation, they could turn into ceremonial knowledge that no one was truly capable of applying. At the same time, some professions would appear aboard the spacecraft that did not exist on Earth. Specialists in microbial balance, rotating habitat engineers, archivists of obsolete data formats, and experts in shield material allocation could all become essential. Language would change with the environment. Words such as rain, beach, or wind might acquire an almost mythical quality. New words would arise for the vibration of machinery, the quality of light during artificial cycles, or locations around the rotating habitat. After several generations, everyday speech might change enough to make the original documents difficult to understand. The community would need to teach its historical language in the same way that people today study ancient texts. Otherwise, the archive of knowledge might still exist while becoming separated from those who needed to use it. Culture would not remain still either. Earth holidays might lose their seasonal meaning. New rituals could form, or the founders would become historical figures. Some generations might honor them, Others might ask why they were given the right to determine the lives of people who had not yet been born. This is the central ethical question of a generation ship. Those who depart agree to the mission. Those born during the journey never gave their consent beforehand. They have no option to return or leave the community. If the mission requires every generation to continue regardless of circumstances, it turns future people into instruments for achieving the goals of the past. A project described as protecting humanity could also take away the autonomy of the people it creates. The community would need the right to reconsider the destination. New data might reveal that the target planet was unsuitable. Another star system might prove to be a better choice. Or the spacecraft itself might have become stable enough that landing would be more dangerous than continuing to live aboard it. Those who departed might see a refusal to land as failure. Those born aboard the spacecraft might see it as protecting their home. Both perspectives would be logical within their own experience. If the destination had different gravity, a toxic atmosphere, or unfamiliar biology, remaining aboard the spacecraft might be safer. The vehicle may originally have been designed as transportation, but after many generations of repairs, expansion, and adaptation, it would have become a habitat. A decision such as changing course would affect people who had not yet been born. A new trajectory could lengthen the journey and consume shielding and other resources. The community could not rely only on the wishes of the current majority while ignoring long-term consequences. But neither could it allow promises made by the dead to lock every possible future in place. Governance aboard the spacecraft would therefore need to connect three groups that could never sit together in the same room: ancestors who had died, people currently alive, and future generations. Its laws would need to protect individual rights, shared resources, and the ability to alter the mission. Professions could not simply be assigned through family lineage. The spacecraft would need doctors, engineers, and growers, but the child of a doctor might not want to become a doctor. If society forced people into roles, it might preserve skills in the short term while creating lasting resentment. The solution would involve broad education, automation, shared responsibilities, and systems designed to be easy to operate. Good technology does more than improve efficiency. It reduces the degree to which society must force individuals into particular lives in order to survive. After many generations, the spacecraft might look completely different from its original design. A new module could be printed from recycled metal. The gardens might expand. The language might change. The first passengers might no longer recognize the society they had created. That would not necessarily be a failure. A sustainable living system must be capable of evolution. Attempting to keep the spacecraft and its society unchanged for centuries might be more dangerous than allowing them to adapt. In the classroom, children look at images of the ocean. In the corridor, an electronic family tree stretches across many sections of the spacecraft. Some of the earliest names list Earth as their place of birth. The newer names have only coordinates from the journey. The destination star grows brighter with each generation, but no one can see the change from one day to the next. It becomes visible only when two images taken decades apart are placed side by side. The spacecraft is still moving from one star system toward another, but to the people inside, that motion is simply a property of their home, just as Earth moves around the sun without the people on its surface feeling it. When birthplace, school, cemetery, and future all exist within the same structure, the spacecraft is no longer merely a vehicle. It has become a world, and that world knows Earth only through light and messages that take years to arrive. Radio waves and lasers both travel at the speed of light through a vacuum. A laser can concentrate energy into a narrower beam and carry data at a higher rate if it is aimed precisely. But neither technology can make information travel faster than C. Even within the solar system, communication delays have already changed the way missions operate. A signal takes more than 1 second to reach the moon. Reaching Mars takes anywhere from several minutes to more than 20 minutes in one direction, depending on the planet's positions. A rover cannot be driven like a remote-controlled vehicle on Earth. It must avoid dangers on its own. A message sent to Proxima Centauri would take about 4.24 years to arrive. An immediate reply would return after a total of nearly 8.5 years. Just 2 spoken sentences would stretch across almost a decade. Suppose the spacecraft sent a report saying, "The primary filtration system is showing unusual behavior. Which replacement design should we use?" The engineering team on Earth would receive that message when the problem was already more than 4 years old. Their answer would reach the spacecraft more than 8 years after the question had been asked. By then, the filter would either have been repaired or the system would have failed. Earth could not serve as mission control. It would be only a library and an advisor sending extremely slow letters. Every emergency would have to be handled locally. The spacecraft would need a digital model of itself, continuously monitoring heat, vibration, pressure, and the flow of matter. Diagnostic software would compare current data with past behavior, predict failures, and recommend possible responses. Artificial intelligence could search the onboard archive, run simulations, and support decision-making. But it would need to explain its reasoning, allow human review, and remain repairable. A system that no one could understand or update might become a mysterious source of authority after several generations. If the AI had been trained using data from Earth at the time of departure, the society and equipment aboard the spacecraft would gradually become different. The system would need to learn from its new environment without forgetting its safety principles. The community would have to control those updates because a software error could spread through every system. Personal messages would create another layer of time. A mother on Earth might record a birthday greeting for a child not yet born aboard the spacecraft. The video could arrive when the child was already several years old. When the child sent a reply, the mother might receive it almost a decade after recording her original message. Neither side would be speaking to the other in the present. Each would be speaking to the future version of the recipient and the past version of the sender. News would behave the same way. An election, a scientific discovery, or a change in Earth's climate would become known aboard the spacecraft years after it occurred. By the time the passengers watched the report, the event might already have produced new consequences whose signals had not yet arrived. The people aboard the spacecraft would never know what was happening on Earth right now. They would know only a sequence of past moments, moving gradually toward the present without ever catching up to it. Signals would also weaken with distance. A broadly transmitted radio wave spreads across an increasingly large area. Its intensity decreases approximately with the square of the distance. Large antennas and narrow beams would help, but aiming at a small spacecraft several light-years away would require extraordinary precision. Lasers could create narrower beams, but diffraction would still cause them to spread. Across interstellar distances, a beam that began extremely narrow might cover a region thousands or millions of kilometers wide, depending on its wavelength and the size of the transmitting aperture. The receiver would need to be large enough and know exactly where to look. Dust, gas, and relative motion would alter the signal's frequency. As the spacecraft moved rapidly away, light from Earth would be redshifted. It would not merely change color. The rate at which the signal arrived would also slow because of the relativistic Doppler effect. At 90% of the speed of light, a steadily transmitting source behind the receding spacecraft would be received at only about 23% of its transmitted frequency, according to the relativistic Doppler factor. A radio signal designed for a specific frequency would require substantial compensation. The spacing between data packets would also be stretched. When the spacecraft turned around or approached a source, the signal would be blue-shifted and compressed. The communications system would need to track the velocity, predict the incoming frequency, and prevent concentrated energy from shifting beyond the safe operating range of the equipment. Time dilation makes the story even more profound. Suppose the spacecraft spent part of its journey traveling steadily at 99% of the speed of light. The Lorentz factor would exceed 7. During a period in which the passengers experienced 10 years, more than 70 years could pass on Earth in that idealized phase of motion. This would not mean that messages automatically reached the spacecraft more quickly from the passenger's perspective. The delay would still depend on the changing distance and the Doppler effect. But the social result would be clear: the travelers might remain young while their home passed through several generations. If they returned, they would not return to the past. They would arrive on a future Earth. Their relatives would have grown old or died. Cities, languages, and institutions might have changed. Time dilation is a form of one-way travel into the future, not a machine for reversing time. Two clocks that once displayed the same time would no longer show the same date when they met again. Each would have measured time correctly along its own journey. An interstellar civilization could therefore never maintain an instantaneous central government across its entire network. Instructions from the center would arrive after circumstances had already changed. Every star system would need a high degree of autonomy. Communication would still have value. It could transmit science, art, historical records, and long-term warnings. Communities could learn from one another, but they could not synchronize decisions the way cities on the same planet can. It would resemble islands exchanging letters, except the ocean between them would be measured in light years, and the islands themselves would move through time at different rates. A society at Proxima Centauri might send a new biological discovery to Earth. Earth would receive it more than 4 years later, study it for several years, and then send back its conclusions. A single generation of scientific cooperation could last for decades after only a few exchanges. Across greater distances, the delay would become even larger. Over 1,000 light-years, a question and its answer would require at least 2,000 years. The original sender and recipient would no longer exist. This would be communication between civilizations across generations, not conversation between individuals. Messages would need to be written so that recipients in the future could understand their context. Language, data formats, and cultural assumptions might change while the signal was traveling. Every data package would need to describe itself, contain instructions for decoding it, and include enough background information to remain usable without relying on obsolete software. An interstellar message would be like a glass bottle released into an ocean of time. It would need to cross more than distance. It would have to survive changes in the people receiving it. Inside the communication compartment, a laser would aim toward the position Earth would occupy when the signal arrived, not the position shown by the light currently reaching the spacecraft. The beam would leave the vehicle, invisible to human eyes, carrying voices and data. During the next 4 years, the sender would continue living. Earth would continue orbiting. By the time the signal arrived, it would already be a historical record. The reply would then begin its journey in the opposite direction. When the spacecraft finally received it, nearly a decade would have passed since the original question. A place might remain physically reachable while becoming separated in time, culture, and history. Communication technology could not keep two worlds within the same present, and even such a vast interstellar network would still lie inside only one galaxy. Beyond the Milky Way, the distances would not merely be greater. Space itself between distant regions would be changing. Relativity also weakens the idea of a single shared present. On Earth, low relative velocities and short distances allow people to use approximately the same calendar. Across interstellar scales, two observers moving differently do not necessarily agree about which distant events are occurring at the same time. This effect is called the relativity of simultaneity. It does not mean that events change arbitrarily. All observers still agree on the order of events that can be connected through cause and effect. But for events too far apart for light to connect them in time, their temporal order may depend on the observer's frame of reference. This means that the question, "What is happening on Earth right now?" has no directly observable answer for someone at Proxima Centauri. They could define a plane of simultaneity according to their own frame of reference, but they could not receive information from that plane before light had time to reach them. In practice, societies would use conventional time systems. Each star system would maintain its own local clocks, exchange reference points, and convert between them using relativistic models. There would be no central clock that the entire galaxy could observe in real time. Scientists could synchronize clocks before separation, and then predict how they would diverge according to their trajectories and gravitational fields. But synchronization would not eliminate the delay. It would only identify where a message belonged within the chosen system of timekeeping. An interstellar report would need to include not only a date and time, but also a position, velocity, and coordinate system. Without them, the meaning of now would become ambiguous. Even on Earth, clocks at different altitudes run at slightly different rates because of gravity. A clock aboard a satellite runs differently from one on the ground. Across an interstellar network, differences caused by velocity and gravity would accumulate on a far greater scale. An interstellar civilization would therefore be divided, not only by politics. It would also be divided by the ways time was experienced and measured. Every community would possess its own history, even while all of them remained part of the same space-time. The Milky Way contains hundreds of billions of stars and stretches across roughly 100,000 light-years. If a signal left one side of the galaxy, even light would need nearly the entire history of modern humanity to reach the other. A civilization could spread at speeds far below that of light. A spacecraft could reach one star system, build infrastructure, and allow a later generation to launch new spacecraft onward. Over millions of years, a wave of settlement could cross much of the galaxy without any individual vehicle ever approaching sea. But such expansion would not create a unified empire in the familiar sense. If two communities were separated by 10,000 light-years, the fastest news between them would require 10,000 years. A decision would become an ancient artifact before it arrived. Every region of the galaxy would live within its own present. There could be no real-time map. A telescope observing a star system 1,000 light-years away would show that system as it existed 1,000 years earlier. A galactic civilization could never know what was happening everywhere at the same time. This is the difference between exploration, settlement, and conquest. Exploration may mean receiving light, sending robotic probes, or making a flyby. Settlement means maintaining life over long periods. Conquest implies control, coordination, and the ability to impose decisions across a wide region. The travel time of light prevents those three things from being equivalent. Humanity may explore many places it never physically reaches. It may settle some places without controlling them from Earth. And it may create a network of communities that no longer has a single center. Beyond the Milky Way, the scale increases again. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away. A one-way signal would require 2.5 million years. A question and answer would require at least 5 million years. 5 million years ago, the genus Homo was still very young. No language, nation, or civilization could be expected to remain unchanged across such a span. Communication between galaxies, even if technically possible, would be an exchange between distant descendants we could not imagine. Andromeda and the Milky Way belong to the local group, a collection of galaxies bound together by gravity. The gravitational attraction between them is strong enough to overcome cosmic expansion on a local scale. It would therefore be incorrect to say that the expansion of the universe causes the distance between all objects to increase. Atoms are not being stretched. Human bodies are not expanding. The solar system is not being pulled apart in any significant way. The Milky Way and the local group are held together by gravity. Expansion becomes clear only across enormous distances between structures that are not gravitationally bound. The universe also does not necessarily expand into some pre-existing emptiness. In general relativity, the measure of distance between widely separated regions changes with time. No central point within space is required for galaxies to move away from it. A common comparison is to imagine dots on the surface of an inflating balloon. Every dot sees the others moving farther away, yet no dot is the center of the surface itself. The analogy is imperfect because the balloon's surface is two-dimensional and has an exterior, while the universe does not require an outside of that kind. Even so, it helps remove the idea of an explosion occurring at one location inside empty space. Within an expanding universe, more distant galaxies generally appear to recede more quickly, as described by Hubble's law. This does not mean that every galaxy moves locally through space in exactly the same way. Individual motions and local gravitational effects still exist. Light traveling through expanding space has its wavelength stretched. Blue light can shift toward red, then into infrared, and eventually, microwave wavelengths. Redshift allows astronomers to infer the history of cosmic expansion and estimate distance within a cosmological model. The universe is about 13.8 billion years old, but the radius of the observable universe is greater than 13.8 billion light-years. Its present radius is commonly estimated at about 46 billion light-years. This may sound paradoxical. How can light have traveled for only 13.8 billion years, while its source is now more than 46 billion light-years away? The reason is that while the photons were traveling, the space between the source and us continued to expand. The present distance is not the same as simply multiplying the speed of light by the age of the universe in a static space. The boundary of the observable universe is known as the particle horizon. It marks the regions whose light has had enough time to reach us since the earliest eras. It is not a wall, not an edge where space ends, and not evidence that nothing exists beyond it. Beyond the current observable horizon, there may still be space, matter, and other regions of the universe. We simply have not yet received information from them. But visibility does not mean reachability. A very distant galaxy may be sending us light that began its journey when the universe was young. Those photons started traveling when the distance was much smaller. During their journey, expansion continued. If humanity sends a signal today, it begins under different conditions. There are galaxies whose ancient light still reaches us, yet a new signal sent now may never reach them if the current model of accelerating expansion continues. This is the cosmic event horizon, the boundary defining which future events can affect us and which events we can still influence. It does not lie at the same location as the edge of the observable universe. The region we can see is larger than the region with which we can communicate in the future. The sky contains places that have sent us their past, but may no longer be able to receive our future. The expansion of the universe is currently observed to be accelerating. The name dark energy is used for the component or effect responsible for this acceleration within the standard model, but its nature remains uncertain. It may be a cosmological constant, a dynamic field, or a sign that the model requires extension. Because dark energy is not yet understood, the final fate of the universe should not be stated with absolute certainty. But if it continues behaving approximately as it does today, galaxies not gravitationally bound to the local group will move farther away, while their new light becomes increasingly redshifted and faint. In the extremely distant future, a civilization may see only the merged galaxy formed from the local group. Much of the universe visible today may become too faint to detect. Without ancient records, such a civilization might struggle to reconstruct the larger cosmic picture that is visible to us now. This creates a beautiful paradox. Humanity cannot yet reach even the nearest stars, yet we live in an era when light from billions of galaxies can still be observed. Our ability to travel is tiny, while the horizon of our understanding is immense. A photon from a distant galaxy may have left its source before the sun Fro. It traveled there via spanning space, past countless objects, and eventually struck the mirror of a telescope on or near Earth. From only a few photons, we can separate the spectrum of light. Dark and bright lines reveal the elements in the gas. Redshift reveals expansion. The width of spectral lines reveals motion. The shape of a galaxy reveals star formation and interaction. We do not need to visit a star to know whether it contains hydrogen, helium, iron, or carbon. Each element absorbs and emits light at characteristic wavelengths, like a barcode written into matter. We do not need to enter a black hole to measure its mass. The motion of nearby stars and gas, X-rays from an accretion disk, and gravitational waves from collisions all carry information outward. We do not need to travel back to the time of the Big Bang. The cosmic microwave background is the remaining light from when the universe was about 380,000 years old. Its tiny temperature variations became the seeds from which later galactic structure formed. Knowledge can extend far beyond physical presence because nature is constantly transmitting signals. Light, neutrinos, cosmic rays, and gravitational waves are messengers from places no spacecraft may ever reach. Observation, of course, also has limits. Signals are weak, noisy, and always carry information from the past. Some regions lie beyond the horizon. No instrument can provide an instantaneous image of the entire universe. But science does not need to possess a place in order to understand it. It builds models from signals, tests predictions, and searches for universal laws. This changes the meaning of conquest. If conquest means planting a flag and governing every location, the universe cannot be conquered. The speed of light, finite lifetimes, and cosmic expansion prevent any single center from controlling everything. If exploration means expanding the region of understanding, the process may have almost no end. Every deeper observation reveals an older layer of time. Every generation improves its detectors and methods of analysis. Within the solar system, humanity may build bases, extract materials, and send robots to other worlds. Such projects remain extraordinarily difficult, but they are not forbidden by cosmic horizons. For the nearest stars, lightweight robotic probes may be the first step. They would not need air, food, or artificial gravity. A laser network might accelerate small sails and send many probes, accepting that some would fail. If a probe reached Proxima Centauri at 0.2c, the idealized journey would take a little more than 20 years, followed by the time needed to accelerate and transmit data home. The first images might reach Earth after several decades, within a human lifetime, but only through technology that has not yet been completed. Human beings would travel more slowly than robots because they would need to carry an entire living world. Perhaps robots would go first, build infrastructure, produce fuel, and confirm the environment. Only afterward would a crewed mission depart. If settled communities appeared, they would become politically and ecologically independent, not because they necessarily wanted separation, but because delay would force autonomy upon them. A galactic civilization might resemble an evolutionary tree. Each branch would leave its original home, preserve part of a shared memory, and then change according to its environment. No central trunk could control every branch in real time. From the perspective of millions of years, life might spread very far. From the perspective of cosmology, even the Milky Way and the local group would still be only a small island. Beyond them, clusters of galaxies form networks of filaments and voids. On the largest scales, matter is distributed like a three-dimensional web, shaped by small fluctuations in the early universe. The interstellar spacecraft that once seemed enormous becomes an invisible point beside the Milky Way. The Milky Way shrinks into a point within the local group. The local group becomes a speck within the cosmic web. The distance between unbound regions continues to increase. Some still send ancient light toward us. Others have already moved beyond the reach of any signal transmitted today. No engine can solve this problem because it is not a matter of power. It is the geometry of space-time. The greatest limit on conquering the universe does not lie in metal, fuel, or the lifespan of the human body. It lies in the fact that there is no single shared present across all of space, that light requires time to travel, and that cosmic distances can increase while a signal is still moving. A civilization lasting long enough might explore the solar system, send robots to nearby stars, form many communities throughout the Milky Way, and receive light from places it could never reach. but it could not stand in one location and instantly control the entire universe. It could not know what was happening everywhere at once. It could not send a signal to every point of light visible in the sky. The universe is large enough to explore almost forever, yet also too large for anyone to possess in its entirety. Human beings may never travel to every light in the sky, yet that light still comes here, entering eyes, telescopes, and detectors while carrying the history of the place that emitted it. A living creature on a small planet may never touch all of space, but it can learn to read the signals traveling through the darkness and reconstruct the story of the universe. Another way to understand this limit is through the idea of a light cone. From any event, light spreads outward in every direction. Places inside its future light cone can be affected by that event. Places outside cannot receive any signal from it without exceeding c. Every person, planet, and civilization has a region of the future it can influence. In static space, that region expands at the speed of light. In an accelerating universe, some distant regions recede so quickly that a light ray sent today will never intersect them. The entire reachable history of a civilization forms a finite causal region, sometimes visualized as a causal diamond, between the past that can be received and the future that can be influenced. A civilization may survive for an extraordinarily long time while still acting only inside its own causal region. Longevity cannot overcome a horizon if distance expands in a way that light cannot catch. This differs from a limit of resources. More energy does not help. A stronger laser still travels at sea. A more durable spacecraft remains inside the light cone. Only if fundamental physics differs from our current models might there be another path, and no experimental evidence presently allows us to rely on that possibility. Even so, our causal region is still immense. It contains the solar system, many nearby stars, and in principle may include a large part of the local group. The final boundary does not make every act of exploration meaningless. It only places a limit on the ambition to possess everything. In the distant future, the local group may become one large galaxy after repeated interactions and mergers. Regions beyond it will become increasingly difficult to observe. Today's astronomical records may become a precious window into an era when the visible universe was much wider. A future civilization may know about galaxies that are no longer observable because its ancestors preserved the data. Knowledge could then survive longer than newly arriving light because it had already been stored within a region that once received the signal. In that sense, observing the universe today does not serve only the present. It preserves part of the cosmos for future ages in which the sky itself may have changed. We can still imagine the original spacecraft resting on its launch pad. White vapor drifts around it, along with chilled pipes and the glow of control panels. Above, the stars appear close together, even though the true distances between them exceed every journey in human history. We have now passed through each of the limits the spacecraft would have to face. Earth's gravity forces a rocket to reach an orbital velocity of nearly 8 kilometers per second. Yet that same gravity keeps the atmosphere and oceans from escaping. The rocket equation causes fuel requirements to grow exponentially because a rocket must accelerate the fuel it has not yet used. The nearest star lies more than 4 light-years away. With present technology, the journey would take tens of thousands of years. To reduce that to a few decades, the spacecraft would need to reach a significant fraction of the speed of light. But the speed of light is not a record like the speed of sound. It is connected to the way space, time, and causality operate. Matter with rest mass cannot reach c using any finite amount of energy. The energy carried by the spacecraft rises rapidly with velocity. A 1,000-ton vehicle traveling at 0. 1c would carry approximately 4.5 times 10 to the 20th joules of kinetic energy, before accounting for efficiency losses or deceleration. Half the journey would be used to create velocity. The other half would have to erase it. Interstellar space is not completely empty. At 0, 1c, hydrogen protons become radiation particles carrying millions of electron volts of energy. An extremely small grain of dust can release the energy of a concentrated explosion when it strikes. The shielding would not remain unchanged. It would gradually wear away like a consumable resource. Radiation could penetrate deeply without leaving a crater. Water, food, and hydrogen-rich materials would need to become protective walls. The life support system could never recycle everything perfectly. A loss of only a few grams each day would become many metric tons over several decades. Filters, valves, microorganisms, and software would all require repair. The spacecraft would need to function as an ecosystem, a factory, and a school at the same time. The human body requires mechanical force. Microgravity causes bones, muscles, circulation, and balance to adapt. Artificial gravity could be created through rotation, but a slowly rotating and comfortable habitat might need to be as large as a city. A community would need more than oxygen and calories. It would need privacy, sleep, fairness, art, and the right to reconsider its purpose. A spacecraft could fail even while its engines continued working, if the people inside no longer believed the journey was worth continuing. A generation ship would pass its mission to people who had never chosen to leave Earth. They might see the spacecraft as their home rather than a vehicle. Science cannot be separated from ethics when one generation's decisions bind the lives of another. Communication could not restore immediacy. A question sent to Proxima Centauri and the returning answer would take nearly a decade. News would always be history. Every interstellar community would need to govern itself. Then the scale expands to the Milky Way, Andromeda, and the cosmic web. A galaxy may remain visible without still being reachable. Ancient light can cross expanding space, while a signal sent today may never catch up with its source. There is no final wall at the edge of the universe. There are only horizons created by finite age, the speed of light, and the expansion of space. All of this may sound like a sequence of closing doors, but that is not the final message. Each limit has taught humanity something profound. Leaving Earth teaches us that orbit is a form of falling. The rocket equation teaches us that mass carries an exponential price. Relativity teaches us that space and time cannot be separated. Interstellar dust teaches us that energy can depend more on velocity than on size. Radiation teaches us that protective material can create new dangers of its own. Closed ecosystems teach us that life depends on cycles, not merely on stored supplies. These limits do more than obstruct us. They reveal the structure of nature. Humanity has never reached another star, yet we know that stars create elements within their cores. We have never set foot inside a distant galaxy, yet we can measure its rotation, composition, and history of star formation. We have never touched the horizon of a black hole, yet we have recorded gravitational waves from black holes merging. The human body cannot follow every photon, but a telescope can receive them. A spacecraft cannot travel to the early universe, but the cosmic microwave background carries an image of that era to us. Exploration does not always require physical presence. Understanding is another way of traveling far. Perhaps one day, small robotic spacecraft will pass through the Proxima Centauri system. Several decades after launch, their first signals may return. A point of light on a screen may become an image of a world orbiting another star. Perhaps much later, human beings will build communities beyond Earth. Not an empire attempting to conquer every place, but branches of life learning how to survive within new environments. Each step will be slower than the dream and more complicated than the slogan, but it may also become more sustainable if humanity understands the limits before attempting to cross them. The spacecraft on the launch pad does not need to carry a promise to conquer the entire universe. It only needs to carry a question worth asking, an instrument durable enough to survive, and the ability to send an answer home. Above it, starlight continues to reach Earth. Some of those rays began their journeys before humanity existed. They traveled through the darkness without knowing that a living creature would one day be waiting to receive them. When that light reaches a telescope, it does not carry humanity to the place where it was emitted. but it brings that place into human understanding. The universe cannot be possessed. It cannot be controlled from a single center. It cannot be observed within one shared present, and no traveler can reach all of it. But it can be observed, measured, and gradually understood by one generation after another. Inside a quiet room, a signal from an extremely distant place is transformed into a small sequence of numbers. From that sequence emerges the temperature of a star, the composition of an atmosphere, or the trace of an ancient galaxy. There is no loud noise. No flag is planted. There is only light completing its journey and a mind learning something new. Perhaps this is the most realistic way humanity can touch the entire universe, not by standing everywhere, but by understanding why each place behaves as it does. The spacecraft may still depart. The limits will remain. But because those limits exist, the journey can teach us more about space, time, life, and our own small place within them. Beyond the thin atmosphere, the darkness continues to expand. It is in no hurry. It makes no promises. It does not need to be conquered. And while light from distant worlds continues falling toward Earth, we can close our eyes, rest, and allow the universe to tell the remainder of its story in its own long rhythm of time.